So two-dimensional dynamic programming are considered to be the most difficult problems, and they are extremely favored by FAANG companies. So today I have decided to create a complete course on 2D dynamic programming problems. We are going to learn everything about what 2D dynamic programming is, how to use it, what are the common patterns, and we will solve 10 most asked, most popular lead code problems. So after this course, I can guarantee you that you would become a master in all sorts of 2D dynamic programming courses. So without any delay, let's get started. So 2D dynamic programming is actually nothing but an extension of the original dynamic programming that we all know. Now, in typical dynamic programming, we are basically given a set of problem that we are trying to solve, and in order to solve that problem, we store the information of all the sub step of that problem in an array or a string like format. So basically, if we have to take the classic example of the climbing stairs problem, basically we are being told that we are given a bunch of stairs, and at any given position we can climb one step or we can climb two steps, and we need to find that how many distinct ways we can reach at the top. This is a classic dynamic programming example, and as part of the solution what we do is we take that if there is only one step, how many distinct ways we can climb at the top. Same way, if there are two steps, how many distinct ways we can climb at the top, and so on and so forth. And we would keep on pertaining that information in an array like format and store it, and then based on that we would be able to very easily calculate the final result only by looking at the previous two values rather than going and redoing the whole exercise. That is the core concept and power of dynamic programming. In two-dimensional dynamic programming, basically we take that up a notch. We typically break the problem down into a pieces of set of permutations and combinations. And let's say that we are given a problem where we are given a particular word and we are given another word. So let's say that is like a substring of the original word one, and we need to find out that how many distinct substrings that we can make out of this second word too that we are given based on this first word. Now in that case, the problem becomes exponentially difficult if we just have to use single dynamic programming. We won't be able to solve it. So what we are going to take it, let's say that for word 1 we are given the values a b a b a b a c, something like this, and word 2 we are given as the value of a b and c. So in this case, what we can do is we can take every single possible combination of word 1 against word 2 in a grid like format. So where we are going to have a scenario that what if we have word 2 present over here, and what if we have word 1 present over here, and for all of the permutations and combinations we would treat that if, let's say for some reason, if word 1 only had values a b and word 2 only had the value a, what would be the total number of substrings that we can generate, and that would be calculated based on a cell value that represents over here, where we can notice that we are currently taking care of a and b from this word 2, and from word 1 we are taking that as if it only has value a. So on and so forth. You can understand all sorts of different questions and examples where we can use 2D dynamic programming. But the core underlying concept is that now instead of just taking care of a single parameter, we are actually worried about two distinct properties, and based on that we are actually going to create a grid like format, and for this grid we are going to iterate over every single combination to solve the problem. Now let's visually represent. For a typical dynamic programming, we saw the classic example of climbing stairs where we had the values being stored within an array. And for any particular value x, the answer of x was directly reliant on the previous two values that we have already calculated, and that was the sum of the previous two values. So let's say that this value was a and this value of b. We could have said that the x is equal to a plus b. This is not going to be as straightforward in a 2D dynamic programming, because now we are dealing with a grid like structure and we already have calculated values beforehand. So let's say that there is any particular cell x that we are trying to work upon. It could be possible that we only care about the direct diagonal value. It could be possible that we care about the top value and the side value, or it could be possible that we care about all of these three values. and some form of addition, multiplication, subtraction, whatever that case might be, would be the recurrence relation in this case to solve this problem. So it is really important in the 2D dynamic programming to first of all understand that number one, what is going to be the base case and what is going to be the recurrence relation. And based on these two information, we need to start populating our matrix to solve the problem that we are currently given at hand. So number one type of problem that frequently occur is any particular grid based problem. So whenever you see that you are trying to deal with two distinct type of character and it makes sense for you to generate a grid to iterate over all the permutations and combinations, definitely this is a clear clue that you can use 2D dynamic programming in order for you to solve this problem. Second one is typically substring related problems. So whenever you are given like two words, you are trying to find all the substrings of one word from the other word, or you are given two words and you are trying to see that how many distinct ways you can generate like word 2 from word 1. All of these things can also be done using 2D dynamic programming. And third one are typically partitioning and permutation and combination problems. So for partitioning problems, it could be possible that we are only given just one set of value, but we will have to partition it in such a way that multiple different form of path are being generated from that particular given value. And for each of the subsequent path, we might have another classic path on their own. And that in such scenarios, we can also start thinking about using 2D dynamic programming. And don't worry, we are going to see examples of all these three. Now, what are the typical prerequisites in order to understand this dynamic programming course? Now, usually I don't put prerequisites in my courses that I teach. But the thing is, this is a special one and this is an advanced level course. So I would highly recommend that first you understand or you have good grasp over the concept of string and array, because this is really important. Now, second thing I want you to learn is to have idea on what typical normal dynamic programming works, because this is going to taking up one step further than we already have. And third thing that you should be familiarized with or have understanding about is that how typically memoization and tabulation works. So these two are typical different ways of iterating over any particular problem, and you need to encounter like recursion and iteration in different scenarios. So you need to understand like bottom up and top down approach and different dynamic programming concepts. So I would highly encourage to have information about these three things. Now I have already created videos and courses on each one of them, so you should be able to find it very easily. Okay, now without any delay, let's get started with the most important part of this course, and that is the 10 most task or most popular and most like LeetCode problems that all belongs to 2D dynamic programming concept. Now I can guarantee you definitely that after these you would be able to solve any dynamic programming problem. So without any delay, let's get started. So the LeetCode problem we are going to solve now is one of the most popular LeetCode problems, that is called best time to buy and sell stocks with cooldown. This one is a medium problem, but in my opinion this can be categorized as hard in some scenarios, and this is a very well liked problem. So let's understand the problem statement. We are given an array called prices that represents the price of any particular stock on any particular given ith day. Now we need to find the maximum profit that we can achieve, and we have the luxury to complete as many transactions as we like. And the only restrictions is that after we sell our stock, we cannot buy the stock for the very next day, which means we'll have to cool down for one day. Now let's try to understand this with an example. Say here are the price of any particular stock is given for 5 consecutive days, and our aim is quite simple: maximize the profit. Now let's try to first understand that what is going to be the answer in this case. Let's say if we decide to buy stock on this particular day, then our buying price is going to be 1, and then we decide to sell the stock on this day, so then our selling price is 2. So what is the profit we made during this duration is going to be of value 1. Then remember, after selling we'll have to wait one more day for the cooldown. So let's say that we decide to cool down on this day, then we buy again when the price is 0, and then we sell again when the price is 2. So we make profit of $2 or 2 units over here. So in total amongst these prices, the maximum profit we can make is going to be 3. Now notice that we did not use the greedy approach and try to maximize our profit in one single transaction. Why? Because logically it would make sense that if we have values like this, then if we have already bought the stock on this day, then instead of selling over here, if we decide to sell on this particular day, then our profit for this region would have been 2, but this would not yield us to the maximum profit. Why? Because then we cannot buy stock on this day because of the cool down condition that we have, and then we are at the last day. So even if we buy the stock, then we are just diminishing our profit. Let's say that we don't do anything on this day, still the maximum profit we can achieve is going to be 2 in this case. So this is a very tricky problem, and first let's try to understand a very simple brute force approach in this case to solve this problem. Now notice the brute force approach is quite straightforward. We, for any particular day, simply try out all the different combinations and permutations and combinations, and do all sorts of calculation. So we can check that what if we buy on this day, then we decide to sell on this day, then we decide to sell on this day, then we decide to sell on this day, and then we decide to sell on this day. Once again repeat the same scenario where we are buying on this day and then selling on this particular day, and based on that also consider it for the cool down scenario as well. So logically, for any particular ith day, we can have 3 different states that we can think about, whether either we are buying, we are selling, or we are resting. And for each one of the 3 possibilities, we'll have to do this ith times, and we are calculating all the permutations, which means now we are talking about the time complexity that yields in big of n factorial time, because we are dealing with all the permutations. So this is a very expensive brute force approach to find the maximum profit. We'll have to optimize the things, but the thing is there is no way for us to get away from maintaining the states for any particular ith day, that what if we buy the stock, what if we sell the stock, or what if we rest for that particular day, and what is going to be the maximum profit in that regard. And once we have this information, it becomes much easy for us to find the appropriate result that we are looking for. Now let's talk about the optimal way that we are going to solve this problem, and we are going to use the most beautiful concept in the computer science, that is dynamic programming. Now let's just do a quick recap. Why do we need to do dynamic programming in this case in order to solve this problem? Well, logically, we cannot use just any single approach to find the maximum profit. We just saw it with this example, that if we decide to use greedy approach, where we are trying to buy at the smallest price and sell at the highest price, this does not yield the correct result. Also, the decision we make at any particular day on whether we need to buy the stock, sell the stock, or go into the cool down mode would depend on the all the previous values we had and all the future calculations that we might have, which means all we can do is that for any particular day we can simply say that if, let's say, on this particular day, if I decide to buy the stock, what is going to be the maximum profit I can make. If I decide to sell the stock, what is going to be the maximum profit, and if I decide to go for the cool down, what is going to be the maximum profit. And keep this calculation doing for every single one of these days, and just based on the previous calculations of the previous day, we should be able to calculate the maximum profit of the subsequent day. So I know what I just said might confuse you, but let me explain it with an example. So let's say that for the same example that we were talking about, let's define each of the scenarios for maximum profit that we need to calculate in each of the 3 scenarios, for buying, selling, and for holding or resting, or if we are in the cool down mode. How do we define that what is the maximum profit we can generate if we decide to buy on any particular day. Let's say that on this particular day, if I decide to buy a stock, then what are the different considerations that I'll have to make? Number one consideration is we can only buy any stock after we are coming out from the cooldown, which means on the previous day we must have been in the cooldown state. So number one thing is, we'll in order to check the maximum profit for buy on any particular day, we will have to compare two values. Number one value is that what was the maximum profit we were achieving on the previous day for this buy operation, and compare it with that what if we did a cool down yesterday and now we are trying to buy. So the cool down maximum profit for the previous day minus the current ith value we have, so price on this particular day. So now let's try to generate the mathematical equation for any particular value of buy. But the thing is, we'll have to remember that what was the maximum profit achieved on the day before, and not on the current day. So for that, we'll need to have some data structure that stores that information, and we can use an array to store that information. We can create an array of the same size. So let's say that I create an array of size 5. Where for any particular day I'm defining that what is going to be the maximum profit I can achieve if I decide to buy on that particular day. So that calculation is going to be dependent on the maximum profit I was able to achieve if I had already bought before and not buy today, or maximum profit I can achieve if I'm coming out of the cooldown and I decide to buy today. So what the mathematical equation is going to be, that maximum profit on if I decide to buy on ith day would be, I'll need to compare two elements. So max between what was the buy of I minus 1. So what was the maximum profit on the previous day, and compare it with the cool down profit on previous day plus sorry, not plus but minus the current prices that we are dealing with. So price on the current day. So this is going to be our mathematical equation for our buy formula. Same way for our selling, let's say that if we want to calculate the maximum profit we can make if I decide to sell on any particular ith day. Once again, I'll have to do the calculation with the previously calculated values. But now in this case, the calculation comes off a bit different. Number one thing is, if I decide to sell today and on any particular day, then the profit I'll be comparing it with is that what is the profit I was making if I sold yesterday. So if I sold yesterday and I made more profit, it does not make sense for me to sell it today. So that is number one thing we are comparing. And we are comparing that what was the buy profit that we made yesterday. So if I bought yesterday, what was the maximum profit I was making plus the price of the current particular day. So same way for the buy we made this equation, same way we can make another equation for sell, where we are comparing the maximum value amongst the two values. So what was the previous profit if I sold on yesterday instead of selling it today, and comparing it with what if the maximum profit I made on buy of I minus 1. So previous day if I bought the stock plus whatever the price of I today is, because the price increased, so there is higher potential that I can gain more profit by selling the stock today. And next thing is, if I decide to rest on this particular day, so let's say that instead of selling on any particular day, I decide that I'm not going to do anything and I'm just going to rest, then what is going to be the implication? So we simply need to compare that what was the previous day's profit we were making, that is for sure. So for rest, we are going to compare the previous day's profit, so rest of I minus 1, and we are going to compare it with what if we sold yesterday. So if we sold yesterday, then we are resting today. So what is going to be the profit if we sell yesterday, and whichever value is maximum, we are going to store that as the answer. Okay, so based on our explanation, these are the three different equations that we made. Now I just wrote them roughly to have a brief idea on what we are talking about. And then we have initialized three different arrays that we are going to play around to keep track of the maximum profit on that particular day based on whether we can buy, sell or rest on any particular day. So now let's first initialize the value, and this is the prices array that we are given, that we are dealing with. Now on first day we cannot sell anything or we cannot rest, so we can mark these values as 0. And the maximum profit we can make on very first day is if we decide to buy something. And let's say if we buy something, we haven't made any profit, we are actually losing money or putting money on the table. So the maximum profit we can make if we buy something is going to be -1 or the negative of the price of that particular day. Okay, now we can start our calculation. So let's say that for second day, if we have to calculate that if we decide to buy something, what is the maximum profit we can make. So for that, for buying, we need to compare the buy price on the previous day, so maximum profit being made on the previous day. And what if we decided to rest on the previous day, so what was the maximum profit we were making then, minus the price of the current day. So if we compare that, we are comparing the value of -1, that is the maximum profit being made on the previous day. And what if we rested on the previous day, so that was 0 minus the price on the current day, so 0 minus 2. So we are comparing the values of -1 and -2. So what is the maximum profit we can make? Well, of course, maximum profit is going to be -1, so we can simply mark -1 at the buy array. Same way for the sell array. If we decide to sell on this particular day, what is the maximum profit we can make? Once again, we are comparing the previous selling profit, previous maximum profit from the previous day, or what if the previous maximum profit we are making if we bought a day earlier plus the prices of the day today. So of course, this is quite obvious that if we decide to compare, then first value we are comparing is 0, because that is the maximum profit we are making on the previous day, and we are comparing it with the buy maximum profit on the previous day, so that was -1 plus the price is today, so the price is today's 2, so -1 plus 2. So we are comparing the values 0 and 1, so obviously 1 is greater, so maximum profit we can make if we decide to sell is going to be 1, so we'll mark 1. Same way, if we decide to rest today, then we are comparing two values, the previous profit being made on rest and previous profit being made on sell. Both of these are previous because we are simply not doing any transactions, we are just resting, so both are 0. So since this maximum profit we can make by resting today is also going to be 0. Next thing is that what is the maximum profit we can make when the price is 3. So once again, for buying we are comparing the maximum profit, so -1 versus what if we rested, so resting is 0, so 0 minus 3 is going to be -3. So -1 and -3 we are comparing, so -1 is the maximum profit, so we'll just mark -1 so far. Okay, now for selling, if we decide to sell when the prices are 3, we are comparing two values. First value we are comparing is the previous day's profit, so that is 1, and second value we are comparing is the previous day, so this is -1, so -1 plus 3, so that is going to be +2. So once again, and by the way, this it would not be this -1 but this -1. I just did not included that, but I hope you understood what I mean. So this profit is going to be 2, that if we decide to sell today, maximum profit would be 2, which would be great. And for the resting over here, we will have to compare the previous day's resting value versus selling value. So this is 1 because we are comparing these two values basically. Once again, when the prices are 0, what is the maximum profit we can make? So now the values we are comparing is going to be -1 with what if we decide to rest yesterday. So if we rested yesterday, then we would have made so it would be 1 minus the current day's price 0, so 1 minus 0 is going to be 1, so we are comparing values -1 and 1. So over here obviously the judgment is quite obvious that it would be in our favor to buy today, so we'll just mark as value number 1. Same way, if we decide to sell today, what is going to be the maximum values we are comparing? Number 1 value is previous day's profit, so we'll mark 2, and second value we are comparing is that what if we bought yesterday, so that is going to be -1 plus the prices of today, so -1 plus 0 is going to be -1. So answer is quite obvious that we are just going to leave 2 as it is. This is the maximum profit we can achieve if we decide to sell today. And for the resting phase, if we decide to rest, we are comparing these two values, so maximum profit we can make is going to be 2. Now for the very last day, the value is 1. So if the value is 1, we are comparing these two values, so first value is 1 and second value we are comparing is 2 minus 1, so both values are 1, so we can make maximum profit as 1, so we'll just leave 1 as it is. Next value is for in terms of selling, what is the maximum profit we can make? So one option we have is 2, because this is what we have. Second option is that the buying profit from the previous day, so this is going to be value 1 plus the price of the stock today. So okay, and this value should not have been 1, this should have been 2. So let me just mark it clear. Okay, so 1 plus 2, so 1 plus 2 is going to be 3. So we are comparing values 2 and 3. So it would be in our favor to sell today if we bought yesterday. So now the answer is going to be 3. This is the maximum profit we can make. And for the very last element, if we decide to rest today, which means we must have sold all of our stocks yesterday. So we are comparing these two values, and the values are 2 and 2. So this is going to be 2. Now this is what our table looks like basically, where we can see that in the end we simply need to check that what is the maximum profit we are making if we are selling on the last day or if we are resting on the last day. Because if we buy on the last day, we are always going to lose money. So whatever value is higher amongst these two value has to be our profit, and in this case our profit is going to be 3. So this is what we can return as it is. So this is the whole solution. I know it looks messy, but it's beautiful in my opinion, because we are, imagine what we are doing. For every single day we are maintaining 3 different states. We are calculating that what is the maximum profit we are achieving on each day, and we are taking into the consideration of the previous task being done for any particular day's solution. So that is in itself pretty awesome that we are able to do it, and dynamic programming is actually giving up a huge contribution in this program. So if we see time complexity now, then it is going to be big O of n, because we are simply iterating over the given input array once to solve the whole thing. If we see space complexity, well, this is going to be big O of 3 times n, because we are initializing 3 new arrays to store all of these states. So this is a beautiful time and space complexity, and also an excellent question in my opinion. So I hope the explanation made sense. Now let's see the coding solution. Now the coding solution for this problem is quite straightforward. First of all, we are checking that if the given prices is equal to null, or the given length of the price array is less than or equal to 1, then we can simply return 0. If that is not the case, we have a variable n that is defined to calculate the length of the given prices array. Based on that, we are going to initiate 3 different arrays to check out the state of the profit on every single possible outcome. So first one is for buy, second one is for sell, and third one is for rest. Now we are going to initialize all of these 3 arrays for the very first position. Now for sell and rest, the value is going to be 0, because it's quite straightforward. We cannot sell on the first day, and if there is no sell happening the day before, then we should not be resting, or this should not be a cooldown day. But for buying, because if we decide to go and buy on the very first day, then definitely we are going to be at a loss. So the maximum profit would be the negative price of that stock and on that particular day. Now we are simply going to run a for loop to iterate over the given input array. We are starting iterating from the very first day, and now we have our condition set up for buy, sell, and rest. In order to make the judgment call that what is going to be the maximum profit if we decide to buy a stock on any particular day, then we will have to compare that what was the maximum profit if we bought the stock the day before, and we need to compare it with, let's say that if we decide to rest the day before minus the current prices on this particular day. Same way, the maximum profit for sell is going to be calculated, where we are comparing the profit from the previous day by selling or by buying whatever we bought on the day before plus the current prices of this day. So we'll compare these two values, whichever is higher we are going to keep that as the profit. And in order to make the judgment that whether we should rest or not today, we will compare the maximum profit achievable on any particular ith day, and for that we are comparing that what if we decide to, what was the profit we made if we rested the day before, comparing with what was the profit we made if we decided to sell the day before. Whichever is higher, we are going to keep it as it is. Now for the maximum profit, we simply need to compare that what was the value if we decide to sell on the very last day, or if we decide to rest on the very last day. Whichever one value is higher, we are going to return that as the answer. So this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully. It beats almost 80% of all the other users, which is pretty significant. And once again, the solution of this code is present in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the lead code problem we are going to solve now is called longest common subsequence. Now we can see that this one is a lead code medium problem and also one of the most liked problems on lead code. So I'm going to pay my utmost attention. Now let's understand the statement. We are given two strings called text1 and text2. Now we need to return the longest common subsequence. And if there is no common subsequence that exists, then we need to return 0. Now we are given the definition of a subsequence is a string, that is a new string that can be generated from the original string with some characters that can be deleted without changing the relative order of the characteristics. So without getting too much into the details of the definition, let's try to understand what we are being asked to solve. Basically, we are given two strings text1 and text2. Now we can notice that text1 currently has 5 characters A, B, C, D, E, and text 2 has currently 3 characters A, C, and E. Now the thing is, if say for an example from text 1 we decide to eliminate this characters B and D, we can also create A, C, and E, and this is going to be the exact same manner, or the sequence of relative order remains the same between both the strings. So we can say that for this given example, we actually have a longest common subsequence that we can make that follows the relative order, and that is of size 3. So we need to return 3 as part of the answer for in this case. Now let's try to understand it with one more example for this one. Now we can see that currently the characters we have is x, y, z, and the characters we have for this text 2 is y, a, b. So now we can only find one character that is common between both of them and that follows the relative order, and that is this y. Apart from that, we don't see anything common. So in this case, we can only create a longest common subsequence that only consists one character. So we need to return 1 as the answer. Now, if we take a look at this example, text1 and text2, we see that there are no characters that are same between both the text. So in this case, we will have to return 0. But in the same example, say for some reason, if we are given the values like A, B, C and D, E, F over here, and then we are also given D, E over here, then we will need to return 2 as the answer, because the relative order of D and E remains the same even if this string had 3 additional characters. So we will have to solve this problem, and definitely this is going to yield to some very interesting results. Now let's understand the brute force approach to solve this problem. The logic is quite straightforward. Let's say that we are currently given two strings in this particular fashion. Then what we can do is we can go through every single possible combination of any particular string and try to match it with the other string. So what I'm suggesting is that for this text one, we start taking permutation of all the other substrings that we can make out of this one. And we know in terms of making permutations, we can actually make 2 to the power of n permutations for any given value. Why? Because at every single character we will have to make the decision that whether we need to include this character or not to include this character in order to generate the permutation. So this would eventually yield us the correct result, because what we'll do is we'll try to create all the different permutations and combination, compare it with this given another string, and we'll try to see that what is the longest common subsequence that we are able to make. But this is very inefficient approach, and also the time complexity goes in some sort of exponential form, so I'll not go into the depths of this one, and we'll try to do something smart in order to solve this problem. Now let me come to the optimal way to solve this problem, and for that we are going to use one of the most beautiful concepts in computer science, and that is dynamic programming. Now let's take a quick recap. Let's understand that why do we actually have to use dynamic programming in this problem. Well, the answer is actually quite straightforward, because let's say that we are currently given the two strings as A, B, C, D, E, and then once again A, C, and E. Now notice that if we start comparing the two strings at any given moment, character by character, it would not be very much fruitful. Why? Because okay, let's say that we define that this A is common between both of the subsequence. Now we are at this character B, and we don't know that next character B is not present over here. So we don't know that whether B is going to be present somewhere down the road or not. So do you think that we should compare B with every other character that is currently present inside the T2 string? Well, we could do that, and we are going to do that. But in order to do that, we'll also have to remember that what was the relative order of sequence that we have been able to identify beforehand. And it could be possible that if we are dealing with multiple sequences, which subsequent to consider. So let me give you one example like this. Let's say that we are given currently strings like a, b, c, d, e, okay, and we are given the t2 string to be a, b, then x, y, z, and then once again we are given the string to be, let's say, b, c, d, e. So do you think that from this particular point forward, if we see, the longest common subsequence we can make is going to be 2? But the moment we start identifying these characters, we can, if we just drop this b, we can actually create the longest common subsequence of size 5. But we have to drop one b that was already part of one of our relative subsequence, which means the result that we are going to make later down the road is actually going to be dependent on the previously calculations that has been made, and also future calculations that we are yet to be make. And when we are at the last position, we should make the best judgment on which path to take. So that's why this is a good candidate for dynamic programming. Now the question is how we are going to use dynamic programming to solve this problem. And for that, what I'm suggesting is, number one, we have to check every single character for all the other characters, and same way for any particular character we will have to compare it with all the remaining characters. So there is no getting away from that in this problem. We will have to do n square work, or m multiplied by n work, where m is the length of text 1 and n is the length of text 2. Okay, so this has to run in big O of n square time complexity. But how we are going to do that? Number one thing I'm suggesting is that we actually create an m cross n grid, just like the one that I have shown over here. And for this particular grid, we'll need two things for our dynamic programming. We'll need a base case scenario. So base case is quite straightforward, that if any particular character is not matching with the other character, then we simply define it as 0. And notice that we actually have created an extra space at the beginning. So there is an extra row and extra column, which means this is not strictly an m cross n matrix. This is actually an m plus 1 multiplied by n plus 1 matrix. So we are adding one more extra line, and that is to consider our base case. Now at any given moment, what we are going to do is, if we identify that there exists a combination, there exists a value that is common. Let's say that over here the C and C is going to be common for this particular cell, which means what we can definitely say in this case is that this cell is going to be an addition to the previously calculated longest common subsequence. Now where is going to be that information for the longest common subsequence? To the diagonal value. Why it would be at the diagonal value? Well, let's take a simple example. Let's say that currently the values are a, b, c, and this value is a, b, and c. So notice that for this particular square, the logic is going to be quite straightforward. We are going to have a and a common at this place, then we are going to have b and b common at this place, and then we are going to have c and c common at this place, which means longest common subsequence is directly represented towards the diagonal value in the best case scenario. And this is the fact that we are going to exploit. So whenever we identify that at this particular location there was a common subsequence, then we had to add one value to the previously found longest common subsequence. But we haven't found any subsequence because this value is 0. So definitely the longest common subsequence at this 8th location is going to be 1. So we are going to mark it by 1. Same way, the longest common subsequence at this location is actually now 2, because we are comparing AB with AB, and that's why this is going to be an addition to the diagonal. So we are going to mark value 2, and same way this is going to be value 3, one more addition. So same logic we are going to apply over here, that whenever we identify any particular common characters, we will check the diagonal value. That is number one thing. Next thing is that let's say we identify any particular character that does not have any common values. So both characters are different than each other. Then it becomes the question that what is the longest common subsequence we have found so far, and there can be two possibilities. Why? Because let's say that I'm currently at this bth position. So on one side I'm checking against AB, but for AB I have checked with A, I have checked with AC, and I have checked with ACE, because I'm trying to fill up this row. Same way for any particular cth character, I'm also comparing it against A, against AB, against ABC and whatnot. So the answer for the longest common subsequence where the characters do not match is actually going to reside on the adjacent cells for any particular cell. So let's say I'm trying to consider the values for this cell. Now we know that B and C don't match. So in this case, we'll have to check that what is the longest common subsequence we found either way, because we are not only comparing text 1 with text 1 or text 2 with text 2, we are comparing them with each other. So we'll have to take the maximum value amongst the adjacent cells, and this is going to yield us the correct result. So now let's recap our rules. Number one, if we find equal characters, so let's say that if an I and j value are equal, then we are going to do the +1 operation compared to its diagonal value. So diagonal value is going to be I minus 1 and j minus 1, this cell. Okay, and if that is not the case, if we find that I and j character do not match, then we will have to find the maximum value from its adjacent values or subsequent neighbors. So now let's try to do the solution right now. Okay, let's start filling up this particular whole matrix. Now very first value we find A and A, there is a match. If there is a match, we are going to compare it with its diagonal value and add 1. So diagonal value is 0, so we are going to add value number 1 over here. Now next thing is that we will also have to check, let's go row by row. So now we are checking this A with this value B. A and B do not match. So if they do not match, we'll have to, for this cell we'll have to check its neighbors. So we check this neighbor and this neighbor, and whichever is the maximum value we add this one. So what we are saying is that up until this point inside our input, we have calculated A B with A. So in this text 1 and text 2, we can see that the longest common subsequence we find was of size 1, and this is what we are defining it over here. Next we are comparing A with C. Once again, A with C, once again there is no commonality, so we'll add value 1. A with D, once again no commonality, so we'll add the maximum value 1. And A with E, once again the maximum value is going to be 1. Now let's repeat the same operation once again, but now this time we are going to be doing it for value C. Now C and A do not match, so we'll try to find the maximum amongst these two value, and once again the maximum value amongst these two is still going to be 1. So let's just mark it as 1. Same way this is going to be 1 as well. Now we are at this position of C matches C, so we'll have to do an increment with the diagonal value, and we are going to be adding +1 over here, so we can mark this as 2. Now for this D with C, we'll have to compare the maximum amongst these two, and the maximum value is 2, so we'll mark the value as 2 as the answer, and same way 2 as the answer over here. Now we are comparing E with this A, so once again the maximum amongst these two values is going to be 1. And notice we found 2 over here, but why we are marking 1? Because notice what we are calculating or comparing so far. We are comparing A with value ACE. So in this case the longest common subsequence is going to be of size 1, and that's why we are marking 1 over here. Same way this is going to be 1 because we are comparing the maximum amongst these two. Same way with C, we are now the value is going to be 2 because this value was 2. And why it was 2? Because notice we are comparing the values ABC versus value ACE, and amongst this comparison we can see that there exists the longest common subsequence of size 2, that is, which is represented over here. This is the beauty of dynamic programming solution. Now for this D comparing with this E, once again we'll choose the maximum, so answer should be 2. And now we have E common for this last cell, so we'll have to do +1 with the diagonal, so 2 + 1 is going to be 3, so we'll mark it as 3. in the end, we simply need to return whatever we find in the very last cell as part of the answer, and that is going to be 3 in this case. So we can return this with confidence. See how beautiful the solution looks. All we need to do is just fill up this matrix and things work out beautifully for us. Now if we have to calculate the time and space complexity for this one, time complexity is going to be big O of n square, or m multiplied by n, and space complexity is also going to be big O of m plus 1 multiplied by n plus 1. So we can say m cross n for simplicity, but anyways, this is a beautiful time and space complexity and very awesome approach. Now let's see the coding solution for this problem. Basically, we are going to define two characters m and n to define the length of both of the given strings text1 and text2. Then we are going to initialize our new array, dp array. Now notice that we are defining it as an length of m plus 1 and n plus 1 to take care of the 0 case scenario that is going to be our base case for our dynamic programming table. Now for this matrix, we are going to fill in all the details. So we are going to use two for loops to iterate over every single row and every single column. Notice that we are starting the values from 1 and 1 because for ith value of 0 and jth value of 0, we already defined the values as 0. Now first thing we are checking is that at any given moment we identify that the character at I minus 1 and character at j minus 1 location are equal to each other. Then for the current ith and jth value, we are going to add 1 to the existing diagonal value, that is I minus 1 and j minus 1 value inside the DP array. If that is not the case, then we are simply going to pick whichever is the maximum value for any particular ith and jth element from its adjacent neighbors. So whether the top value or the left value of any given cell. And in the end, we should have completed all the values for the longest common subsequence, and the very last element inside our DP array is going to represent that. So we are simply going to represent that value. That should give us our correct longest common subsequence. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 90% of all the other solutions. That is excellent in terms of time complexity. Now for the memory, we can improve on some aspects, but we are using like an m cross n grid, and that is also a fine enough solution. But overall, this is a beautiful solution, and once again, it is available on our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called coin change 2. This is the additional version of the original coin change problem. Now we can see that this one is a medium problem and also a very well-liked problem. The statement is quite straightforward, that we are given an integer array called coins that represents the coins of different denominations, and we are also given an integer amount called amount. So that represents the total number of money that we are trying to make. Now we need to return the number of combinations that make up to that amount, and if we cannot make any particular such combination, then we need to return 0. Now let's try to understand this with an example. Suppose we are given an input where the coins we are given are currently 1, 2 and 5, and we are given the amount to be value number 5. Now the ask of this problem is to see that using these coins, how many different ways we can generate the total amount to be 5. So let's start marking each of the ways. Well, one way is quite straightforward. If we use all 5 1 coins, then we can actually make up to the value number 5. Second way is if we use coin number 2 plus we use 3 1 coins. So this is also a good way, and we can generate value number 5. Same way we can use 2 coins of 2, and then we can use 1 coin of 1. And the lastly is that we don't use 1 or 2 coin, and we simply use coin number 5, and that also gives us value number 5. So in total there are 4 distinct ways for us to generate value number 5. So in this case we will return 4 as the answer. First and most common approach that comes to our mind is a brute force solution, where we are given coins and we are trying to find different ways to make any particular amount. So let's say that in this case the amount is 5. What is the most common thing that we can do to solve this problem? That is that we will take every single coin and try to make every single possibilities. So one possibilities, we will take this coin number 1 5 times to generate amount number 5. Then one possibility is that we will take this coin number 1 4 times and then we will add this coin. Then we will take this one coin 3 times and then we will add this coin 1. Same way we will keep on repeating this again and again and again for every single possible combination. And you can see that eventually we would receive the correct result of 4, but this brute force approach is going to get out of hand really quickly, because now we are dealing with exponential time complexity and we are working in the like realm of factorial and exponential time and space complexity. So this is a very bad approach. Now, in order to generate the optimal solution, we are going to use the most beautiful concept in the computer science, and that is called dynamic programming. Now, first, let's understand that what is the core logic to finding solution for any particular coin in this problem. Let's say that currently we are only given the coin of size 2 and we want to find out that how many distinct ways we can generate amount number 8. Well, for sure in your mind must be saying that there is only one distinct way to generate amount number 8. But let me take a different approach. Let's try to see that if starting from 1, how many different ways we can generate each of these amounts, and we will try to make some important assumptions based on the findings that we are going to make. So let's say that currently we have all of these values. Now we know that currently if we only have the coin number 2, we cannot generate amount number 1. So let's say that currently we cannot generate amount number 1, so we can mark this as 0. Also, no, remember one thing, that we are at the beginning of our input, so we don't have any way to generate each of these amounts. So initially I'm going to initialize all of these values with zeros. Now I know for a fact that if I have coin number 2, I can always make value number 2. So I can simply mark this value as 1. So let me just mark this as 1. Now I also know for a fact that I can also generate amount number 4 using coin number 2. So let me also mark this value as 1 as well. And now let's do a recap. Why was I able to mark this value as 1? Because one logic is that I can do 2 plus 2. But other logic is that if I already know I need to do 2 plus 2, why am I bothering to doing all of these computation when I already know that how many distinct ways I can generate amount number 2? Because whatever the number of distinct ways I can generate amount number 2, I just need to add the total number of distinct ways for the amount number 4 that I'm currently doing. I know it sounds confusing, but let me give you an example. Let's say that currently in order to generate amount number 6, I only have 0 distinct way to do it. But now I know that currently I'm dealing with coin that is of value 2. I also know that the current amount I am trying to make is amount number 6. So I can simply check that if I do 6 minus 2, so in this case, the value is going to be 4. I simply need to check that whatever the distinct ways I can make value number 4, I just need to add it to the current number of distinct ways I can generate value number 6. And that is going to be the number of distinct ways I should be able to generate value number 6. So in this case, this value is going to be 1. Same way, currently I can not generate value number 8, but I know I have a coin of size 2. So instead of doing all of these computation like this, I can simply check that 8 minus the value of amount of coin is going to be 6. I can generate 6 one distinct way. I can generate 8 0 distinct ways. So why not just do 6 plus 8, like whatever the sum of these two values, and whatever the value is, that is going to be the new value for 8. And this becomes our dynamic programming solution to solving this problem. And we are going to do this for every single coin, because in our initial example, we only had one coin of value number 2, but now we are going to have a coin of 2 and 1 and 5. If we have scenarios like this, how would this operate? So this is the core logic we are basing our solution based on. Now let's make some considerations for the optimal solution. Number one, we are going to be using a dynamic programming array to store the result from the starting value of 0 all the way up to the current amount that we are given. Now the first question is, what is going to be our base case? And that is quite straightforward, that if we have to generate amount 0, we know for a fact that there are 0 distinct ways to generate there is one distinct way to generate amount number 0. So we can mark this as 1. Next thing is that in order to generate any particular dynamic programming of I value, the answer is that we are simply going to check that what is the current distinct way to generate any particular I, plus we are going to be doing dp of I minus the current coin that we are iterating over, and that is also we are going to be adding into the number of distinct ways. Using this one solution, we should be able to find the result of this problem and all the different possible ways to generate the answer. So let's take it with one example and it would make things more clear. So let's say the given coins are 1, 2 and 5, and the currently amount we are trying to make is 5. So now we are going to initialize our dynamic programming array, and now we also have our base case that there is one distinct way to generate amount number 0. Now we are dealing with coin number 1. So for coin number 1, we are going to be using the same logic, and we will start iterating for value number 1, because whatever the coin size is, we will start iterating from there. So now currently all of these values are 0 because there are 0 distinct ways to generate value number 1. What is going to be the equation of dynamic programming of 1 in this case using this logic? This is going to be dynamic programming of 1. So currently this is 0 plus dynamic programming of 1 minus the current coin value, that is 1. So dynamic programming of 0. So this value is 1. So remember from over here. So we can just take it from here and this value becomes 1. So we will mark this initial value as 1. Now same way we are going to be repeating the same operation for dp of 2. So dp of 2 is going to be dp of 2 plus dp of 1. So this value is also going to be 1, and same way subsequently all of these values are going to be 1 for our coin number 1. So let's just mark all of these values as 1. Now again, now we are dealing with another equation and another coin. Next coin in our category is coin number 2. So let's say that we are dealing with coin number 2. So for coin number 2, we will start iterating from coin number like amount number 2, because it does not make sense to iterate from amount number 1. What is going to be equation for dp of 2 in this case? This is going to be dp of 2. So current distinct ways to generate amount number 2 plus dp of 2 minus the amount, the current coin value, that is 2 minus 2, so that this is going to be 0. So this value is already 1 because we already have one distinct way to generate amount number 2, plus we will also check it over here. So now we have 1. So notice now we have two distinct ways to generate value number 2, and we are dealing with coins 1 and 2 possibilities. So in this case this value is going to become 2. Same way we are going to be, this 3 is going to remain as it is, because 3 minus, remember 3 minus 1 is going to be 1. 3 minus 2 is going to be 1, but the thing is this value is also 1 and this value is also 1. So this is also now going to become 2, because now there are two distinct ways to generate amount number 3. For value number 4, this is we are going to be doing sum of these two values. So now once again 4 is going to become 3, because there are three distinct ways to generate amount number 4. And same way for value number 5, now we are going to be doing the sum of 5 plus 3. So this total is going to be 1 plus 2. So now there are three distinct ways to generate amount number 5 as well. Now we are bringing in the value number 5 into the equation. Now for the value number 5 would not impact all of these results up until this point, because we cannot add 5 for anything, but we can add 5 for this value. So for what is going to be the equation for dp of 5, this is going to be current dp of 5 plus dp of 5 minus the value of current coin. So current coin value is 5, so 5 minus 5 is going to be 0. So this is going to be, there are three distinct ways that we took from here, plus there is going to be one distinct way that we can make amount number 5, and that is going to be over here. So the answer is going to be 4. So in this case we can just mark this value as 4, and this is going to be the whole solution. Now see how beautiful this solution is, and all we have to do is just come up with this equation and try to understand that how generating a new value based on the previous value using the current coin size can make all the difference. And this is the whole solution basically. So now let's move on. Now let's understand the time and space complexity first. Time complexity is going to be big O of n square, and not n square, big O of n. So where n is the given number of coins multiplied by the amount that we are trying to calculate. So overall we can consider it as n square because it's like multiplication of two different variables, but one variable is the number of coins and the other variable is the amount that we are trying to generate. And in terms of space complexity, it is going to be big of n because we are using an additional array to store all the results. Now let's move on to the coding solution. So for the coding, the idea is quite straightforward. First, we are going to initialize our dynamic programming array to the value of amount plus 1 because we need to encounter for the value 0. Now we will set up the base case for our dynamic programming, where if you have to create amount 0, there is exactly one way to make amount 0 using no coins. And then we will keep on updating our dynamic programming array for every single coin. Logic is quite straightforward. First, we will take in the current coin that we are iterating over. Then we are going to start iterating from the value of coin to the value of amount, and for every single value for that particular instance of j, we are going to add it based on j minus coin. So whatever the current value is, we will add it with the j minus 1 location, and in the end we should only return the amount that we are being asked to return. So whatever value we find for the dynamic programming amount, we can simply return that. So such a small coding solution, but such a beautiful approach using dynamic programming. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats 100% of all the other solutions, which means this is the most optimal solution that we have provided, and also this is one of the most efficient in terms of space complexity as well. So once again, this coding solution for this problem is available on our GitHub repository. Feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called target sum, and we can see that this one is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. We are basically given an integer array called nums, and we are also given an additional integer called target. Now we need to build an expression out of these given numbers such that by adding one of the plus and minus syllables before each of the integer in numbers and concatenating this expression to basically create this target value. So here is an example. Let's say that if we are given values 2 and 1, then we can add plus before this 2 and we can add a minus before this 1 and combine them to build an expression such that minus 2 plus 1, which is going to result in the value 1. So now we can basically create bunch of different expressions like this using plus and minus sign. Now we need to return the different expressions that we can build inside the given nums array, there where the total sum becomes the target, and we need to return every single possible combination that can have such values. So let's say if we are given an example like this, where we are given nums array that contains 5 elements and all the values are 1, and we are also given a target value that sums up to 3. Now in this case, we can use plus and minus symbol to create bunch of different expressions that I have noted down over here, and we can see that all of these are unique operations that all sums up to value number 3. And in total we can define that there are exactly 5 different ways for us to generate value number 3 from using this given nums array and using plus and minus equation, and in the end we need to return 5 as the answer in this case. Now first let's try to understand the very preliminary brute force approach. The logic is quite straightforward, that for any particular given number of input, all we need to do is just test out every single possible plus and minus symbols and make the subset sum of every single possible permutations and combinations. Let's say in this case we are given target to be 3 and we are given these 4 values. So what we'll do is first we will use all the plus values and we will try to see that if we are able to reach target. If not, then we will try to go reverse and we will try to add one minus over here and then leave all of the values are plus. Then we will make these two as minus, then we will make these three as minus, then we will make all four as minus, and so on and so forth. We will keep on checking bunch of different permutations and combinations. Whenever we hit target value, we will mark that as an correct answer, and in the end we simply need to return that variable. This solution works. it gives the answer, but it is extremely inefficient, and you can understand why. Because we are testing every single potential permutation and combinations, and majority of time we are going to be not targeting value number 3, we will have some other answer, so we are not focused on that. So we'll have to do things smartly. So before we come to the optimal approach, let's make few things or few mathematical equations correctly. Let's say that we are currently given bunch of different values inside our nums array, right? Now we know that all of these values, they can have some any particular meaning. The thing is, we can add all of these values and we can mark these values, so sum of all the values inside a variable called sum. So let sum be the sum of a plus b plus c. Now we are also given for a fact that we need to create partition amongst these a, b and c in such a manner that there are two partitions. First partition is s1 and second partition is s2, and the difference of these two partition becomes the target value. So this is one equation we can make. Second equation is sum of s1 plus sum of s2 is actually going to be this sum value as well. So now we have two mathematical quadratic equations for two different variables, and we know the value of target, we know the value of sum. So it should make sense for us to get the quantifiable value for s1 and s2, and let's combine them. So if we do combination of these two plus this two, we can create a new equation where the values are, we did nothing special, we just did sum of these two values. Okay, now in this scenario, this s2 and s2 are going to cancel out each other, so we can say that 2 of s1 is going to be target plus sum. So we know that we need to find a partition such that the value s1 exists, and the value of s1 is going to be simple, that is going to be target plus sum divided by 2, and we have the value of s1. Now if we can identify s1, then we should be able to identify s2. So s2 would be basically all the remaining values, and we will just add minus sign before them. Now the thing is, lucky for us, we are not being asked to calculate that what are all the different expressions. We simply need to provide the number of different expressions. So for that, we actually don't need to calculate every single possible pairs. We simply need to know that what are different ways we can generate s1, and this would be true for s2 as well, and then we can simply return that as the answer. Okay, so now we have established all of these things. Now let's try to also consider some edge cases and some scenarios that for sure we can say that they are never going to make anything. So let's say that if we identify that sum of all the values are less than 0, in this case it would be impossible for us to generate the target value. So in this case we can simply return 0 as the answer. Same way, if we identify that the value of s1 is not modulo by 2, it's not possible to modulo by 2, then also we can return 0. Next thing is that in any scenario we identify that s1 value becomes is a negative value, then also we cannot find subsequent s2 value, because in front of s2 we are putting all the negative values, so we can return 0 as well. These are going to be our edge cases, so we can get rid of them. Now let's come to the meat of the solution. The aim is that we are currently given a nums array that contains bunch of different values. Let's say a1, b1, c1, all of these are some integer values. Now we need to create the combination amongst these values such that the sum of them, so a plus b could become s1, or a plus c could become s1, so on and so forth. We are not focused on adding plus or minus and all of these things. We are only focused on finding a subset sum amongst the given values that sums up to that value. And this is the critical moment of the entire problem, to understand that why are we trying to find this one. Okay, now we know what we need. Let's see how we can achieve this, and how is actually going to be solved by the most beautiful concept in the entire computer science, and that is called dynamic programming. Now why dynamic programming is a good candidate in this case? Well, reason is quite straightforward. Let's say that we are currently only given just one value, 1, and we are given some arbitrary target value. So in that case we can simply say that whether this makes the target or not, does not make the target. Let's say the target is also 1, then we can say that there is exactly one way to generate target, we can clearly see. But if we are given values 1, 1 and 1, now in this case the number of ways we can generate target actually increases with the increment of every single value. Let's say next value is 2, let's say next value is 4, so on and so forth. Whenever new values gets added to the equation, the way for us to generate that particular target becomes increasingly more. On top of it, our S1 also changes. So what I'm suggesting is that instead of focusing that how many different ways we can generate S1, why don't we just generate the entire sequence that starting from 0 all the way up to S1, that how many different ways we are able to generate that particular element, and that we can calculate very easily using every single numbers that we are given. And we are going to keep into the consideration that how many different ways we were able to generate some previous element, and based on that we would add that value to our S1. So that's why this is a good candidate for dynamic programming. On top of it, let's see that how does dynamic programming is actually going to work. So we explained that we are going to create a dynamic programming array. We also know that how can we generate our S1. Basically the formula for S1 is the target plus total sum divided by 2, and we simply need to generate this value. Now for our dynamic programming, we are going to have an array that starts from 0 and goes all the way up to our S1. Now what is going to be the value of dp of 0? No, now notice that this 0 indicates that how many different ways can we generate value 0. And in this case we know that there is exactly one way we can generate value 0, and that is by not using any values inside our subset sum problem. So there is one way, and this is going to be our base case that we can use as like a stopping point. Now let's say for an example, I'm giving scenario. Let's say that the given number only contains value 3, and the target we are given, let's say that this target is also 3, right? Now we know for a fact that if this number is 3, then we can make two numbers plus 3, and we can also make minus 3, because we can use two signs plus and minus. So in that case, if this number is 3, does it make sense for us to check that how many different ways we can generate value 1 and 2? No, of course not. We cannot generate value 1 or 2 using this value 3. We can only generate value 3 and above values. So we are always going to be considering this value 3. So what is going to be our dynamic programming equation? Dynamic programming equation is quite straightforward. Let's say that if we are trying to find that what is going to be the dynamic programming of 3, because current the given number is 3, then this is going to be that how many number of different ways we are able to generate 3 plus the total number of difference between dynamic programming of 3 minus the current num value. So current 3 that we have, so basically 3 minus num, and this would be the formula that we are going to be using in order to populate our dynamic programming array. Let me explain the solution once again, that at any given moment dynamic programming of ith number is going to be depending on dynamic programming of ith, which already says that these are the different ways you can generate value number I plus dp of I minus the current num value that we are iterating over. Because remember, if we can generate 3, we can also generate 6, like if we are given one more 3, so on and so forth. So if we are at 6 location and we know that there are two different ways we are able to generate 3, then there is going to be 3 different ways we can generate 6. Basically that's the way how it works. Let's say assuming that original value of 6 was 1. Now coming back to our problem, let's try to populate our dp array for the given case. Let's say that current given values are 1 1 1 1 and 1. So in this case all of these values are 1, and the target value we are currently given is going to be 3. Now for this scenario we are going to be using our equation that dp of I is going to be dp of I plus dp of I minus num's value, and we need to calculate our S1. So S1 is going to be target plus sum. So in this case target is 3 and the sum is going to be 5. So let me just mark sum is equal to 5. So S1 is going to be 5 plus 3, 8 divided by 2. So S1 is going to be 4. So we are going to initialize our dynamic programming array that is going to be extending from value 0 all the way up to 4. So let's just mark this value. Okay, now let's start making our base case. So dynamic programming of value 0 is 1, so that is obvious. we can't do anything about it. Now let's start populating all of these values one by one. Now the current value we are dealing with is value number 1. Now notice that we are actually going to start traversing in the reverse order, not in this order. And why are we going in the reverse order is to make sure that whenever we calculate the results or the number of subset sum, we calculate that only once, not two times. Because let's say that if in this case currently all of these values are 0 0 0 0. Now if I apply this equation and if I start with this one, so position 1 we are going to be starting with, then this value becomes 1, this value becomes, now this value would become 2. Why? Because we are doing the sum of this value with this value, and so on and so forth. So the value would keep on increasing and we would count the same value multiple times. So that's why we will start counting in the reverse and we will come up until this particular number value that we have. So let's start with value number 4. Currently the value of value number 4 is 0, and currently so this value is going to be 0 and dp of I minus none. So 4 minus 1 is going to be 3. This is also 0. So we are not bothered to check or update this value number 4, because there are no ways we can generate value number 4 using just 1. Now next, once again we are at dp of 3. So for that, and we are considering this very first one so far. Now once again equation is going to be 0 plus dp of 3 minus dp of 2. So 0 plus this, so this value is also going to be 0, so this will remain 0. Same way dp of 2 will also remain 0 because this is 0 plus 0. But for dp of 1, dp of 1 is 0, but dp of 1 minus num is going to be 1. So this value becomes 1 at the end of this equation. And notice that what we have done so far is nothing but just saying that if we are only given an input array that contains value 1, then we can only generate value or target sum to be 1 time. That's it. Now we are considering our scope and we are including the second one into the equation. Let's repeat the same operation. So dp of 4 is still going to remain 0, and same way dp of 3 is also going to remain 0 because of this equation. But for dp of 2, now this value would become 1 as well. Why? Because now we have one way to generate value number 2, that is by using 1 plus 1. And for dp of 1, this value will become 2. Why? Because remember that we are following this equation, so this is going to become 1 plus dp of I minus num is also going to be 0, and that value is also 1, so this value would become 2. Okay, after this, now we are considering this third one. So once again the value of dp of 4 is going to remain 0, so let's just leave it as it is. But for this dp of 3, this value is going to become 1. So let's just mark this one as 1. Now dp of 2 is going to become current value of 1 plus 2. So this value is going to become 3. So let's just mark this as 3. And this value is going to become 2 plus 1. So this is also going to become 3. So let's just mark 3 as well. Now we are considering this one. So for this particular one, now once again we are starting from position number 4, and this value is actually going to become 1 because the previous value is 1. Now this value is going to become 1 plus 3, so because previous value is 4, so let's just mark this one. This value is going to become 6, so let's just mark this one, and this value is going to become 4, so let's just mark this one as well. Okay, cool. Now we are at the final one. So for the final one, we are going to be doing the sum of these two values. So this value would become 5, which means we are saying that if we have to generate 4 using these values, then we have 5 different ways to generate 4. Same way this value is going to become 10. So let's just mark this as 10, and let's just mark this as 10 as well. And in this case 1 would become 5, and this one is going to remain 1 as it is. And now we have reached to the end of all the nums. So basically we are simply going to return this value as it is. This is the whole solution. Now look how beautiful this looks. Basically this dynamic programming array tells us that if we are given the input numbers as 1 1 1 1 1, then If we are given the target value to be 4, then we can generate it in 5 different ways. If we are given target value or s1 value, not target value, if s1 value to be 3, then we can generate it 10 different way, and so on and so forth. So we are calculating for all the possibilities, and I hope my solution made sense. Now let's understand the time and space complexity. Time complexity is going to be simply big O of n multiplied by big total number of s1, because we will have to do every single iteration this time for all the values that are currently present inside our given input nums. In terms of space complexity, because we are using an additional array, it is going to be big O of n, but that is a reasonable and acceptable solution. It's not that bad, and it's actually pretty good because we are using memoization to solve this problem. So now let's see the coding solution for this one. So first we are going to create a variable called sum, and then we are going to iterate over the given nums array to include the total sum of all the elements, and that we are going to populate inside our sum variable. Now we are checking that if it is possible to make partition, which means we are checking few edge cases and scenarios. That is, the first one is that if the sum of target plus sum becomes an odd number, then we can simply return 0. If that is not the case, then if the sum is actually total sum is actually less than the absolute value of target, in that case we can also return 0 as well. If that is not the case, we are going to define our s1, that is defined by target plus sum divided by 2, based on the explanation we had during our solution. Now we are checking that if the s1 is less than 0, then also we can return 0. This is to make sure that we are preventing negative array size. If that is not the case, then we are going to initialize our dynamic programming array, where we are initializing it with s plus 1 plus 1 value, and we are going to have our initial base case for our dp array, where dp of 0 is 1, because there is exactly one way to sum up to 0 by using no elements. Then we are going to iterate over every single nums that is currently present inside our nums array, and for each of the number we are actually starting from s1, and we are coming down all the way up to nums, and we are reducing one value. So there is a loop inside the loop, where we are simply following the equation, where the value of dynamic programming of j is going to be the sum of dynamic programming of j plus j minus num. And we are coming in reverse order in the second loop, is to make sure that we are not counting the same element twice. If we go from num to s1, then there is a very high likelihood that we are going to keep on counting the same element multiple times, and that would give us all kinds of weird results. So in the end, we simply need to return dp of s1, and this should give us the total number of distinct ways we can sum up to that particular target element. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats almost 99.78% of all the other solutions, which is our solution is one of the most popular solution on the entire LeetCode, which is pretty awesome. And we are also extremely efficient in terms of space complexity as well. So once again, the solution for this code is present in our GitHub repository. Feel free to go ahead and check it out from there. Thank you. The LeetCode problem we are going to solve now is called edit distance. We can see that this one is a LeetCode medium problem, and also extremely well-liked problem on LeetCode. Basically, we are given two strings, word1 and word2, and we need to return the minimum number of operations that we need to do in order to convert word1 into word2 completely. Now we have three operations that we are allowed to do. We can insert a character, delete a character, or replace a character at any single moment, and we can come up with the solution. So let's try to understand some of the examples on how long will it take. So let's say that if the given word1 is horse and word2 is Ross, in this case we'll need to do three operations basically to convert this word1 into word2. First, we will convert this h into r. So now we are left with two words, basically RORSE and then ROS. Then we will keep O as it is and R as it is. Now we can delete this R. So notice that now we have the two words as ROSE and ROS, and then lastly we can also delete this E. So basically we have both the words same. So notice we did three operations. First one was the replace operation between these two values. Then we simply go ahead and deleted this R and then deleted this E, and that solved the problem. Same way, if we are given three words like A, B, C and XYZ, in this case the only thing we can do is we can replace each of the character one by one. So in this case we also need to complete or take three operations to come up with this solution. Let's say if we are given two words that are exactly same, so in this case we don't need to do any operation and we can simply return 0 as the answer. So basically the idea is that we have the ability to either insert, delete or replace a character, but we'll have to convert word 1 to word 2 basically. So now let's try to understand that what would be the brute force approach to solve this problem. So in this case, as a brute force, at every single character we have the three probabilities that we can choose for, and we can replace the character with whatever character we have over here. We can delete this character, and we can create an or we can insert a new character. So we can take each of this subsequent path, and then over there we will also have three more possibilities, and we would continue to keep on going down each of the path until we find word 2, and we will find all the possibilities of generating word 2, and whichever has the smallest distance we will pick that. Now notice that this is a very expensive brute force solution. Why? Because at every single node we have possibilities to go down to three other nodes, and even for those three nodes we have subsequent more possibilities. So basically we are running into issues of exponential time complexity, and that would directly be dependent on the total number of words present for word 1 and word 2, which is very expensive. So we'll have to find a smarter and clever way to come up with the solution. Now logically the only thing that makes sense in this case would be that because we are dealing with word 1 and word 2, and we are dealing with all the values that we currently have. Now notice that whatever the result that we have computed so far would impact on the subsequent result we are trying to generate. I'll repeat what I just said. Basically currently if we have to generate like A, B and A, X and Z from this given A, B, then what possibilities we have? Like we know that first character is A, so we can keep it as it is. Now we are dealing with generating this B with this remaining X and Z. And for that what we can do, so with the B we will have basically a character, so we can just replace it with X, and then we can insert Z over here, so we can generate an answer like this. But the thing is, notice that we don't know subsequently in word if this value was to A B Y Z. If it was something like this, then we would have our choices differ. If we had some other values where we are trying to come up with a solution where let's say that this is A B Z, and the next value we are trying to build is A X B Y Z. So even in this case, every single moment we are trying to make the decision, we will have to compute that what was done for the previous values and take that into consideration. And I am giving all of this explanation just to explain that we will be using the most beautiful approach to solve this problem, that is using dynamic programming, where we will compute every single possibilities. So we'll compute that if we have to generate this word and the only word given is currently A, what would be the answer? A B, then what would be the answer? A B Z, then what would be the answer? And so on and so forth. If we try out every single permutation combination and have a 2D matrix to keep track of all of these values, then we'll be able to solve this problem very efficiently. Now what are the possibilities we have at any given location? Remember, we can do three operations. We can do an insert operation, we can do a delete operation, we can do a replace operation. And for each of the three operation, if we only do this operation if the current characters that we are dealing with for the word 1 and word 2 do not match. So let's say if they do not match, we need to do these three operations, but we are only going to be selective, and we will look at the previously computed results from our dynamic programming array. And for that we would be able to determine that if we do insert, if we do delete, or if we do replace, what is going to be the cheapest operation? And we will do +1 because we are adding one more operation, and then compute the result. Now let's try to understand this with an example, and it would make much more sense on what I'm talking about. We are going to take into the consideration for the same input that we were originally dealing with, where word 1 is horse and word 2 is Ross. Now notice that I have created one additional row and additional column on the each side, and that is to take care of the scenario of what if word 1 is completely empty and what if word 2 is completely empty. And based on that, we will build our solution, because remember, for dynamic programming we need two things. We need a base case and we need a recurrence relation. So base case is what if the word is completely empty, then we know that we will have to only insert the character and build the solution. And recurrence relation is the 3 subsequent neighboring cells that we have already computed for any particular cell that we are trying to compute. So let's see a scenario like this, where presumably word 1 currently is null, and we know that, let's say that given word 1 is null, and for the word 2 that value we are given is also null, then we basically do 0 operations, because we can't do anything to, because they both are exactly same. Now if word 1 is still null, that is what this row defines, but word 2 contains the value only R. Now if word 1 is null and word 2 is R, if we want to generate R from word 1, what will we do? Basically we would insert a character, so we would do one operation, insert operation, where we are inserting a value, and that is what we are doing over here. So in order to generate only R subsequent with the given current empty word 1, we would need to do it with one operation. Same way, if we have to generate RO and this word 1 is null, we basically insert two characters, so we are going to do two operations. Now notice in this case we don't need it to compute for this full value, because we already know that in order to generate R we only needed to do one operation. If we have to generate O, we know for a fact that for to generate R there is only one operation needed. So for RO we only need to consider the maximum number of operations needed to generate R +1, because we are inserting a new character, and that is supposed to be 2. Same way for ROS, we are not going to compute the full thing, but we know for in order to generate RO it takes 2 operations, and then if we have to add S to it, it adds one more operation, so this is going to be 3. Same way, let's imagine that for this particular first column, if the given word 2 is, let's say, null, and the given word 1 is, let's say, all of this HORSE, horse, then what we would do in order to generate this value? Well, if it's going to be null, we can add it as 0 because both values are same. But if this word, same way, if this word 2 is equal to, let's say, null, and word 1 is currently H, then basically we will have to delete H, because we are trying to build word 2 from word 1. So in that case we will have to do one operation. Same way, if we have to basically given word 1 as HO and word 2 as null, once again we will have to delete H and delete O. But we don't need to calculate how much time it takes in order to do both of this. We already know that it takes one operation to delete H. Same way it's going to take 1 + 1 operation to delete HO. So this is going to be 2. Same way this is going to be 3, 4 and 5 subsequently. Now notice that at every single character that we are trying to build, we basically have 3 possibilities. Let's say that currently word 1 we have is, so for this case this is going to contain value H, and word 2 we have is only going to contain value R. Now in this case, for both basically H and R, if we want to generate this, what are the options we have? For word 1 we can either replace, delete or insert a character. And if we were to replace a character, basically we simply take whatever the previous value we had over here and we just replace it. We do the replace operation. That is option number 1. Second option is, if we have to delete the current character, if we have to basically, if we are trying to delete this H, then this is the scenario where H does not exist, only R exists. So we take whatever the value we have over here and do +1 over here, because we did a delete operation. So that would be the subsequent value over here. Or if we have to insert a character, basically in that case R does not exist. So in this case, once again we take whatever the value we had over here and do +1. So now notice that in order to build this cell, we have three corresponding relations with each of these three subsequent cells. We can do whatever operation we want to, but basically in each of the cases, our number of operations we are doing relies on the subsequent neighboring cells. So if we do +1 amongst these three, then basically we can generate that value. But the thing is that +1, we are going to pick the minimum cost it takes to build this cell amongst these three. So for these three values, we will do +1 and we will see that what is going to be the minimum value, and whichever the minimum value is, we are going to insert that value over here. So I hope that logic is understood to you why we are picking this value. But basically in this case, notice that if we do +1 over here, the value becomes 2. This also value becomes 2. But in this case, this would turn value to be 1. So we are going to keep value as 1. Now notice same way, this character is H, this character is O. Once again, they do not match. And because they do not match, we have the option to do all of these three operations. They depend on the neighboring cells. The neighboring cells we already know. So once again, we will do the minimum amongst these three. So the total is going to be 2, and basically +1 with the minimum. Same way for this one, the minimum +1. So the total is going to be 3. So what does this 3 defines? This defines that if we have given word 1 as H and word 2 as basically ROS, in order to do that, if we have to do that, it takes 3 operations to build that this word ROS from this word 1H. Same way we are going to be doing for every single possibility and combination. Once again, now notice O and R do not match. So we will do the minimum operation. So minimum is going to be 2. Once again, now in this case, because this O and because this O match for this particular cell, if there is a match, we don't need to do anything, and we can just take previous subsequent diagonal value we had, where basically we are not doing anything, we are just keeping the value as it is. So this is going to be 1. Same way, if we have to do this now, because the values do not match, so it's going to be 1 + 1, so this is going to be 2. Same way for this R and R, because these values match, we will take the diagonal value 2. Once again over here, the sum is going to be 2, and once again for here, the sum is going to be 2, and that is this diagonal sum. Okay, same way for this S and R, the values do not match, so this will become 3. S and O, once again values do not match, so this would become 3. Now S and S do match, so because they match, we will take the diagonal value and keep 2 as it is. Now same way for this particular cell, the value is going to be 4. For this particular cell, the value is going to be once again 4, and for this particular cell, the value is going to be 3. And whatever the last value we have on this 2D array, that would basically define that if the word 1 was the full value, so HORSE, and if the word 2 was the full value ROS, then it would take 3 operations to build word 2 from word 1. And we can return 3 as the answer. So this is going to be the whole solution. Now if we see time and space complexity, in this case the time complexity is going to be big O of m multiplied by n, because we'll have to iterate over every single value that is currently present. And in terms of space complexity, well, because we are using an additional 2D array, this is also going to be big O of n multiplied by n. But overall, this is much better than our brute force approach, and this is a beautiful example on how dynamic programming can be powerful for us to solve any problem, especially like the recurrence relation problems. Okay, so let's try to see the coding solution for this now. So the coding solution is quite straightforward. Basically, we are going to define two variables m and n to capture the length of word 1 and word 2. Then we are going to initialize our 2D dynamic programming array that is going to be of size m+1 and m+1, where we will need to create a scenario where m and n are defined as 0, and then we will find values for those as well. Then we will initialize our value for basically each of the words. So like for word 1 and word 2, if they were given alone, and then we will try to fill in the values for both word 1 and word 2 in subsequent first row and first column. After doing that, we will fill in the rest of the dynamic programming array, where we are iterating over every single cell that are not filled, where we are checking that if the given subsequent word 1 and word 2 are same, then we will just choose whatever the previous value was from the diagonal value. If that is not the case, we will check all the 3 adjacent neighboring cells plus 1 and try to find the minimum value for each one of them. So basically we will try to replicate the scenario on if we have to delete a character, replace a character, or insert a character, and whatever is going to be the least cost, we would put that in the current I and jth value. In the end, we simply return the result or the very last element inside our dynamic programming array, and that should provide us the distance it takes for to generate word 1 from word 2 or vice versa. So let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this. And our code works well and beats most of the other solutions in terms of time complexity, so which is pretty good. And once again, the coding solution would be present on our GitHub repository, so feel free to go and check it out from there. Thank you. The LeetCode problem we are going to solve now is called interleaving string. Now this one is a LeetCode medium problem, a very well-liked problem. The thing is, this problem statement is extremely complicated to understand. We are given string s1, s2 and s3. Now we need to check that whether string s3 is formed by interleaving strings s1 and s2. If you want, you can go ahead and read this all of this description. If not, let me give you a quick simple example. We can notice that currently the entire S3 can be created using the characters in the same sequence that they are present in S1 and S2. So let's take it one by one. We have this character A. So we can take A from S1. So we use this one. Same way we use A. So we also use this one. Now we have a D. So currently this character is B and this is D. So once again we can use this one. Same way now we have B, B and C. So we can use B, you can use B, and we can use C. So same way we use all of these characters, and then once again we have characters B and C, and same way we have character A. So we can take A from here, and then once again we have one more C, and then we can take C from here, and this ends all the characters inside S1 and S2 and all the characters inside the S3. We can say that we can interleave string S3 from the given string S1 and S2. This is what we need to prove for any given input. If we are able to do that, awesome, we need to return true. If we cannot do that, we need to return false. Well, the most basic brute force approach comes to our mind is to check for every single permutation and combination of S1 and S2 to see that how can we form all the characters in such a way that we are able to generate S3. So let's say that we are checking for the first character A. Then we need to either choose the first character over here or first character over here. We cannot choose both. So lucky for us, we can choose A over here. So we get rid of this character. Now we are at second character on B and we are still at first character at B. Now the thing is, next character we are trying to find is B. Let's say that by sheer chance we decided to choose this B character. If we choose this B character, immediately the very next element is X. Thing is, we check, okay, this one is B and this one is C. So X does not match B or C. So we can say that because this does not match either one, we can simply return false, saying that we cannot interleave string. But thing is, this would be a wrong assumption because we did not consider the scenario where instead of picking this B, we could have picked this B, and then we would be still in a position where we are comparing the values between this B and this X, and then this X would have made perfect clear sense. So in the simplest term, we are actually making a decision tree where the very first character option choices we have is amongst A and B, which is the very first these two characters. And for that we have in the S3 we have a character A that we compared. So now we get rid of this one. Now in the next choice we have the characters B and then once again B, and in the S3 once again the character we have is B. The thing is, we don't know which B are we going to choose from. So we can choose from B that is located over here, and then we would have the choices C and B, or we could have chosen this B and then once again the choices we would have is going to be B and X. So depending on that, we can have many different decision trees. And now you will start to notice the problem that could arise, because at every given moment we have the option to select something from between two different tasks or two different paths. And that is the time complexity of 2 to the power n, which is extremely bad time complexity. And that's why solving this problem in brute force would yield the correct result, but this is not going to be a good approach. We are trying to deal a scenario such that any particular result that we are currently calculating is actually going to have an impact on the previously calculated results, and depending on that we will have to make further decisions that which path are we going to take. And this is why this becomes a perfect candidate for the most beautiful concept in the computer science, that is called dynamic programming. Because number one, we will have to keep track that what was the previously calculated result. Number two, what is the current result. And number three, store these values in such a format or such a fashion where we can access them immediately, and we can make judgment calls based on that. So let's start understanding with very small examples. Let's say s1 is an empty string, s2 is an empty string, and s3 is an empty string. Once again, yes, from using this example we can create string s1 from s2 and s3. This is always going to be true. Let's take one more complicated example. Let's say the values are going to be a, b, and this value is going to be c. And currently for s3 we are comparing the values a, c, and b. We know we can make this one, but how it is going to work? The idea is, first we are going to compare the very first element compared to s1 and s2 and the value s3. And for that, let me just make a very small table. Okay, this is going to say that if I am at 0 and 0th position, then even for the s3 I'm going to check for the 0th value. If I am at first and 0th position, then for the s3 I'm going to check for the first value. If I am at second and 0th position, then 2 plus 0, so I'm going to check for the second value inside the s3, and so on and so forth. We will keep on repeating and compare the values. So let's compare. We know if we are at 0 position and 0 position in s1 and s2, and the cell inside the s3 is also 0, so currently we are starting at 1. 0 means that s1 is empty, s2 is empty, and s3 is empty. In that case, this is always going to be true, because we can always interleave string s3 from s1 and s2 if both characters are 0. Okay, that's a given fact. Now let's take this scenario. Currently we are at position a. So let's say that if we are only given s1 is equal to a, we are only given s2 is equal to nothing, because we are marking it as 0, and 0 we don't have any value for s2. And for s3 we currently have we are only comparing the 1 plus 0, so we are only comparing the first value inside the s1. So currently s3 also contains just a one value. So if this is the case, are we able to interleave string s3 from s1 and s2? Yes, we can interleave string s3. We can just use this string. So because these two values are same, we can say that this is going to be true. Now let's add one more scenario. Let's add this 2 over here. So if we are given a string such that a, b, s2 is still empty because we are comparing against this cell, and for s3, because this has two characters, we are going to mark two characters. So this is going to be a and c. Now in this case, are we able to interleave string s3 as ac if the given string s1 is ab and s2 is empty? No, because b and c does not match. So in this case we can mark, because they do not match, we will mark this result as false. Okay, if that is, now let's come back. Now we are at this position, so we are checking for this particular cell. So what is the position of this cell? Currently this one is empty, so the value inside the s1 is going to be empty, and the value inside the s2 is only going to be c. And we are comparing the s3 to be so let's do the sum of these characters, because this is 0 and this is 1, so we are only comparing one value from the s3, and that is going to be a. So if we are given three strings s1, s2, and s3 like this, are we able to interleave? No, because this one is a and this one is c, so they do not match, so we are going to mark false over here. Now once again let's repeat the same operation. Now we are checking in for this particular cell. So what are going to be the configurations for the cells s1, s2, and s3? Well, s2 S2 is going to contain character C, S1 is going to contain character A, and for the combination of this one, so this is 1 and this is 1, so 1 plus 1 is 2, so we are going to consider two characters from S3, and that is going to be AC. In this case, we know we are able to generate this pair completely, so we know for sure that this needs to be true. The thing is, how are we able to say for certainty that these pair matches? Well, because notice, and this particular position, we have the value, this value as A, this value as C, and the combination of these two values becomes AC. Let's see that what is matching with what. We can see that very first value A, we already have a match because of this particular value, and currently we have a match with C that is coming in. So whenever we have any value on, like this is going to be y axis, so whenever we have any match on, let's say that this is going to be our ith row and this is going to be our jth row, if we have a match on jth row, because C is matching with this current C, so if we have a match on jth row, we will have to compare that are we able to generate A and C in order to make sure that if this C is valid or not. If you get confused, just look at this example and it would make sense, because we can, this character C is only good if we already have a previously matching character. If we did not have a previously matching character, let's say over here, instead of this S3 being ABC, if we had values XCB, then this would have been XC. So even if these two characters match, because we are at this particular cell, still this should not have been true. Why? Because this character did not match, and if this character did not match, this value would have been false. So in this case, because this value was true, so using that, because this value was not X and this value was actually A, then only we can say that there is any fruitfulness in this C currently matching with the subsequent value inside S3. So the result of this character is actually dependent on its previous character, because the string was from S2. So whenever any particular cell from S2 we are trying to compare, we are going to check it with the previous element on top of it. So in this case, we can mark this one as true as well, because this character was true. Same way, now we are at this position where if we notice, this is going to be A, B, C, and since the sum is going to be 2 plus 1, so 2 plus 1 is 3, so we are going to compare all of these three characters, so this is going to be A, C, B as well. Now notice that the matching pair in this case is actually going to be this B. So we are matching with the character from S1. If we are matching for this particular cell for a character from S1, then we need to check that whether the very previous value for all the other remaining S1 characters, are we facing the value to be true. And in this case, because remember, same way for this character, we check that whether this previous element was true or not. And because this element was true, then only we can say for certainty that this has to be true as well. But in this case, now the matching pair is from this region, the top region, then we will have to check that whether for this cell, whether its previous element on the left for S2 was true or not. Why? Because let's say, once again repeating the same example, let's say that if this S3, instead of being ACB, if this value was, once again, let's say XCB or XYB, something like this one, then even if this B matches, the previous values did not match, so this value must have been false. So then we would have to mark this false. But since this was not false and we found out a correct match, so we can also mark this as true. Now we iterated every single possibility inside this cell, and same way we simply need to return whatever the value we have at the very last element inside this character, and then we can return it as true or false. Now let's take one more quick example to understand that how does this thing is going to work completely. So for this example, we know that this value is always going to be true, so let's just mark this as true. Now we are going to iterate over the first column. Okay, so we will compare the only S1 values with S3 values. So for this first value, we have a matching. So because, and because it's s1, we are comparing it with its previous value, so currently this matches, so we can also mark this a as true. Same way, next value is b. Once again, ab and ab are still matching, so and the previous value is true, so we can also mark this one as true. Next value is x and this value is c. Because of this, they do not match, so we are going to mark this as false. We don't need to check any other value. Next value is once again b and this value is d, so once again they do not match, so we can simply return false. And even if they did match, we would still mark them as false because the previous value was false. Same way, we are going to check the column value where we are only comparing this s2 with this given s3. So currently the very first value should have been a, but over here the value is b, so we can mark this as false. Same way, now this value is b, but this value is x, so once again we can mark this as false. And same way, this value is y, but this value is x, so once again we can mark this one as x. Now we are at position 1 and 1. So because values are 1 and 1, we are comparing the value number 2. So value number 2 is going to be b. So we can see that yes, there is a potential match b over here. Now notice, whenever there is a match on this side, we will need to compare for this cell, it's above cell above it. So since this value was true, we are going to mark this value as true as well. Now we are comparing once again this particular cell. So for this cell, the value should be 2 plus 1. So we will need to compare the third value. So third value is x over here, and over here both values are b and b, so this value needs to be false. Same way, next we are going to compare 3 plus 1, fourth value. So fourth value is b. So we notice that over here we do find a potential match b with this b, fourth value that we are trying to compare. But the thing is, once again, same way, yes, we have a potential match over here, but the value above this was false. So because of that, we are also going to mark this one as false. And same way, now we have this value c over here, and we have this value comparing between d and b, so it does not match, so we are going to return false over here. Same way, now once again we are comparing this particular cell. So now the value is 2 plus 1, so 3. So third value is x. Yes, because third value is x, we can notice that this x matches. It matches with the value on once again j axis, so we will have to compare the value above it. This value is true, so because of that, this is also going to be true. Then we are going to compare this b and x with this b. So once again, this value is b, that is correct. Now this b matches with the value over here. In this case, because it matches with the value on the y-axis, we, for this particular cell, instead of covering the value above it, we are going to check for the value right before it, and this is true, so that's why this is also going to be true. Next, we are going to compare the values between c and x, and this value is 3 plus 2, 5. So fifth value is going to be the c. So once again, this c is true. So if this, because it matches with over here with the ith value, so we are going to compare the value before this one, that is true, so we are going to mark this one as true as well. Same way, the next value we are comparing is going to be d and x, and over here the value is also d, so we are also going to mark this one as true because it matched over here. Now we are at once again this position, the value is y, so the value is 3 plus 1. So 3 plus 1, 4. 4 is not y, so we can y, or 4 is not a, so we can simply return false over here. Same way, this value we are comparing is going to be b with y. So and this is going to be 2 plus 3, 5. So fifth value is actually c over here, so we can return false over here. Same way, now this is going to be 3 plus 3, so sixth value is d, and over here the values we are comparing are going to be y and c. So once again, it does not match, so we can return false. And the very next value is y, and because this is the seventh value and we are comparing 4 plus 3, seventh value over here, so we have a potential match y. The moment we see a potential match y on this jth axis, then we will have to compare the value above, and the value above is t, so this value is also going to be true. And in the end, we need to return whatever the value we found for the very last element. Since this was true, we are going to return true, and this is the whole solution. See how beautiful the solution is, because for every single possible pair, we keep on checking that whether we can interleave string s3 with given subsequent string s1 and s2. So this is pretty awesome. And the time complexity in this case is going to be big O of m multiplied by n, where m is the length of s1 and n is the length of s2. Space complexity is also going to be big O of m multiplied by n, and it is quite obvious because we are using a dynamic programming 2D array to store this answer. So now let's quickly see the coding solution. The coding solution is quite straightforward. First, we are going to define three different variables m, n, and l to define respective lengths of s1, s2, and s3 strings. We will check for an edge case that if the given string length m plus n is not equal to l, we can return false immediately. If that is not the case, we will initialize our dynamic programming array, and notice that as part of the length, we are keeping it as m plus 1 and n plus 1. This is to take care of that extra row and extra column where we are only considering s1 or s2 string. Then we are going to have our base case that dp of 0, 0 would be true, as in we can always create or interleave a string with 0 characters if both s1 and s2 has 0 and s3 also has 0 characters. If that is not the case, then we are going to fill in the first row where we are simply going to check the values for the s1 row, and same way we are going to fill in our first column using s2. Where we are simply comparing the characters s1 and s2, s1 with s3 and s2 with s3, and we are going to pick the previous row value or column value in the place of the current ith or jth position. Then we will fill in the rest of the DP table where we are going to use two for loops starting with I equal to 1 and j equal to 1, and for every single cell we will compare that whether that cell matches with s1 and s3 or it matches with s2 and s3. If it matches with s1 and s3, then we can simply mark the value of the previous row position. If it matches with s2 and s3, the character value, then we will mark it with the previous column position, and based on that we will keep on filling our DP table or dynamic programming table. In the end, we can simply return the value for DP of m and DP of n. So if this is true, it's great. If it is not true, then we can simply return false. And this is the coding solution. Let's try to run our code. Seems like our solution works as expected. Let's submit this code. And our code beats good chunk of other solutions in terms of time complexity, and it is excellent in terms of space complexity. We beat nearly 96.46% of all the cases, which is pretty awesome. And once again, the coding solution is present in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the question we are going to do today is called longest increasing path in a matrix. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Apple, DoorDash, Google, Facebook, TikTok, Nvidia, Amazon, Uber, Microsoft, Snapchat, ByteDance, and bunch of more. So I'm going to pay my utmost attention. I hope you also find this useful. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to find. Basically, we are given an m cross an integer matrix, and we need to return the length of the longest increasing path in this given matrix. Now, how do we build this longest increasing path that we need to return the length of? Essentially, we are told that from every single cell, we can move in 4 directions: left, right, up, or down. And based on that, we need to calculate that what is going to be the longest increasing path. We are also explicitly told that we don't have to care about diagonally moving or values outside the boundary. So let's try to understand this with an example. Suppose in this case, this is the example that we are given. Now our aim is to find the longest increasing path. Now we know that from any single cell, how to define an increasing path. Let's say that we are currently located at this cell number 4. Now we have the option to go in 4 direction: up, down, left, and right. Now from this 4 direction, we only need to go to the direction of the cell that is actually increasing order. So we need to maintain this increasing property. So from this value number 4, what are the places we can go? We can go to 9 and we can go to 8. We cannot go to 6 because this would be a diagonal, and we cannot go anywhere outside the boundary. Now in both the cases, we have the option that the values are currently in the increasing order for this 8 and 9, which means both are legitimate scenario. But our aim is to find the longest increasing path. So from 8, do we have any other option to go to that increases in the path? No. From 9, do we have any other option to go to in any next cell that increases? Again, no. So in this case, from 4, the longest increasing path we can make is going to be 2. But is this the longest inside the given entire matrix? The answer is no. We need to find the cell that has the longest increasing path. So if we take one more example, let's take an example for this value number 1. Again, at this location value number 1, we have the option to go into 4 direction. But let's say that for the ease of convenience, we decide to go into the direction of this 1 to 2. Currently, the increasing path length is 1. Again, from this 2, we have one more neighboring cell that is higher than the value, that is this value number 6. So this time the increasing path value will increase by 1. And again, from the 6, we can go to one more neighbor that increases in the value, and that is value number 1. And originally we started with this value number 1 and we moved one hop. So basically we will add one more over here. So essentially we can create a path that looks like this, 1, 2, 6 and 9, and this would be the longest increasing path in our matrix, and the length of this matrix is going to be value number 4. That is what we need to return in the answer. And the first approach comes to our mind is the brute force approach, the very basic approach that we can take to solve this problem. Now let's try to understand that what would be the brute force approach in this manner. Well, of course, the answer is quite simple. From every single cell, we start iterating in all 4 directions, and from all 4 directions we will see that where we can find the increasing path, and the moment we find the increasing path, we keep on adding the value to our answer variable, and we will keep on adding 1 over here. And same way for our increasing path, we will go to its neighbor, and again we will keep on repeating the same process. So let's try to see the solution I'm proposing in action. Okay, so let's say that for the ease of convenience, we start at value number 1 or this value number 9. Again, from 9, what would be the increasing path we are able to make, and what is the maximum answer we have find so far? These are the 2 variables we are going to keep track of. So 9 does not have any neighbors that are in the increasing order, because 9 is the biggest value amongst all. So in this case, we won't be able to find anything. Let's go to this another 9. Again, same thing will happen. We won't be able to find anything. So these 2 are the values that we took care of. Now we are at value number 4. Since value number 4, we already calculated that there are only 2 paths we can take. So currently the increasing path maximum we can make is going to be 2. So answer currently we have found so far is value number 2, that this is the maximum path we are able to make. But let's keep on increasing with next subsequent values. So currently the values we took care of is going to be the first row. So I'm just going to mark them as X, that we already took care of this. Now we are at this value number 6. From 6, what are the options we have? We cannot go here because this is not increasing, this is same. We can go here to 9, so this is good. So from 6, we can again create a path of increasing path of size 2, and then that's it. So again our answer will remain same. We also took care of 6. Same goes for this 6. This 6, we have the option to go to value number 9, and we have the option to go to value number 8, but that won't lead to any further results. So again we cannot move anywhere forward. So we also took care of these 5 variables. Now let's move on to value number 8. Again, from this value number 8, we do not actually have any path to go to, so we don't even bother updating any of the variables. Now we are at value number 2, and now things will start to get a little bit interesting. So what are the options for the increasing path we have at value number 2? So first increasing path option is over here. So from 2 to 6, that is good. Again, from 6, do we have the option to go for the increasing path? And the answer is yes. That is 6 to 9. So in this case, from this value number 2, the maximum increasing path we can achieve is going to be value number 3. So we are going to update our result, and so far the longest increasing path we have found so far is going to be value number 3. So again we are going to update our answer as well. Now we are at value number 1. So what are the options we have so far? Can we go to this? No. Can we go to this 6? Yes. So currently we go to this 6. From this 6, what are the options we have? We can either go to 9 or we can either go to 8. So let's just first go to 8. Okay, now we went to the 8. From 8, can we go anywhere else? No. So in this case, for this particular path, the answer we found is 3. But we still have one more option, that from 6 we can still go to this 9. So even if we go from 6 to 9, we don't have anywhere else to go. So once again, the answer is going to be 3 as well. Now after taking care of both of these paths, now let's explore more options, and that option is that from this 1 we can go to this value number 2. Okay, from this 2 we still have option to go to value number 6. From this 6 we still have option to go to value number 9. So in this case, we created a path that is 1 to 2 to 6 and then to 9. So in this case, we created a path with a path length of 4. That is going to be the maximum path we have found so far. So we are again going to update our values. So this is going to be the current increasing path we found for the cell number 1, and the maximum path we have been able to find is also going to be 4. So we are going to update our answer because we need to enter the longest increasing path. And now we still have one more value that we need to go to. So again, from this value number 1, we have the option to go to 1 to 8. And then from 8 we won't be able to go anywhere else. So in this case, the maximum path we are able to achieve is going to be 2. After completing or after iterating every single value, we found out that the maximum longest increasing path we can create is going to be value number 4. So our brute force approach gave us the appropriate answer that we were looking for. But was it the most optimal answer? Well, the answer you already know, that of course not. And why? Because there are a few things we can actually make changes to. So first thing we can make change to is going to be regarding that for every single cell we were actually doing a lot of repeated computation, and how we were doing that, let me give you a quick example. So again, let's clean this up a bit. Initially, when we were traversing our answer, when we reached to this value number 6, we already knew that from this 6 there is only one path we can go, and that is going to yield us the higher result, and that is from 6 to 9. So the longest increasing path, or the longest path we can make at value number 6, was going to be 2. Now when we came back to this value number 1, originally from 1, what we did was we went from 1 to 2, from 2 to 6, and 6 to 9, every single place repeating the computation we have already completed, and that is a bad approach. What if we already knew that at value number 6 the longest we can do is going to be 2? Same way, this value number 2, the longest we can make is going to be value number 3. So based on this information, if we are at value number 1 and we need to go back to this value number 2, we can clearly see that from 1 we already know that there is an increasing path that leads to 2, but from 2 we already know that the maximum amount of value it can generate in terms of longest increasing path is going to be of value number 3. So rather than doing all of this computation, we could have actually just done from 1 we reach to 2 and see that we already have the computation result for 2. So we could have done 1 plus 3 and the answer would have been immediately available to us as the value 4. So this is one of the major significant improvement we can make. And what this improvement is, this is actually we are storing the results that we have already calculated. So what we are doing is one of my favorite things and one of the most beautiful things that is available in the computer science, that is we are actually using dynamic programming in this case. But on top of using dynamic programming, we are also doing something more interesting, and that is that we are actually rather than treating this as the matrix or 3 by 3 matrix, we can actually treat this as individual nodes, and this individual nodes would have some way of connection with them. How connection? Because we are trying to find a path. Now for this path we are actually given the definition that if only from this current cell, let's say the value of current cell is A, if there is a path from A to B where B is greater than A, then only we can connect A to B and consider it for our path. So rather than treating this as just 2 by 2 matrix or m cross n matrix, we can actually consider every single cell in this matrix is equal to node and the path that we are trying to connect actually as the vertices. And once we do this, After seeing these two words, immediately in your mind it's gonna click that essentially we are treating this as a graph solution, and we are in the graph we are trying to find the longest increasing path. We already know how to build a path, and that is using the greater than or less than relation between any two cells. So essentially we already have a directed graph, and we already know that there won't be any cycles in this graph, because let's say that how does the cycle occur in a single graph? Let's say we go from 3 to 5 up in the same position 3, then we can see that there is a cycle. But in this case it is not possible to have a cycle. Why? Because the relation of this edge is actually based on the property that 3 is less than 5. That's why there is an edge that exists over here. If 3 was not less than 5, then there won't be any edge over here. So which means from 5 to 3 there is an edge, there is an impossible way to create an edge. So essentially this is also going to be an acyclic graph, and we already know that this is a director acyclic graph, and in the DAG or directed acyclic graph we are trying to find the longest path. Basically, rather than treating it as longest increasing path, we are just trying to find the longest path. So essentially now our life becomes much easier. On top of that, we are already going to use the dynamic programming properties. So we are going to know that how we are going to take care of every single value. So we are not going to repeat the computations that we have already created. Now let's see that what would be the solution look like in action. Okay, so now what we are going to do is we are actually going to create a dynamic programming to m cross n grid, and in this case we are going to use this to store that every single element, how many increasing path we can make, maximum amount of increasing path we can make. So this would be a great help for in terms of memorization. On top of that, for every single node, we are treating it as a graph, and we are going to build the graph upon them. So we are not actually creating a separate graph. We can actually use the same matrix. For the visual representation, I'm going to make some circles and some arrows, but you would be able to imagine that what we are actually trying to do. So first, let's say that we are at value number 9. So we are at a graph node like 9. From 9, do we have any edges extending out? No, because this is the same as 9 and this is less than 9. So there is no edges, which means the longest path we can make at value number 9 is going to be of value number 1. Okay, we are good with this result. Now at this second cell 9, again same thing is going to happen, that we are going to have a single cell that is not able to branch out or connect with anything else. So once again the longest path we are going to make is going to be value number 1. Now we are at this value number 4. What are the options we have? So let me just clean this up a bit, and from this value number 4 we actually have a couple of options. We can either go from 4 to 9, or we can go from 4 to 8. So let's say if we decide to go from 4 to 9, do we need to calculate that from 9 how many values we can go to? No. Why? Because we already know this result. So from this 4, let's say if we decide to go to 9, we are actually going to create a path like this, that initially we are going to have a node 4, and from 4 we have the option to go to 9, or from this value number 4 we have the option to go to value number 8. So currently we have two options. From this 8 we don't know how many options we have because we haven't calculated, but we already calculated the result for this value number 9, which means if we decide to go from 4 to 9, we are for sure guaranteed to have an increasing path of 2, because from 9 it does not lead anywhere else. So we are good with this so far, which means and from this 4 to 8, let's say if we decide that from 4 we are going to go to 8, what are the options we have? From 8 we cannot go here or here. So again from 8 there are no possible nodes that we can calculate, which means we are again going to be able to create a maximum path of 2. So in this case, rather than doing all of this computation, we can actually store our answer, and we can just put down the value 2 over here, that this is the longest path 4 can take. Now we are at position number 6. From 6, what are the options here? It has, well, 6, as you can clearly see that 6 is not able to go over here. It is only able to go over here, and this we have already calculated from. So that means that from 6 we only have two options, and that is the longest path we can make is of value number 2. Again, from this 6 we have two options. We can go to this value number 8 or we can go to this value number 9. In either case, the maximum path we are going to make is going to be of size 2. Reasons you already know. From this 8 we cannot actually go anywhere else, so the longest path we will be able to make is going to be 1. Now from this value number 2 we actually have just one option that where we can go, and that is to go to this value number 6. But from this 6 we already calculated the results, and that is going to be 2. So in this case we can clearly write the answer as 3. Now from this 1 we actually have multiple options to go to, so this I'm going to draw in the answer and you would be able to understand what I mean. So initially we are located at this value number 1. From this 1 we have the option to go to value number 6. From this 1 we also have the option to go to value number 2, and from this 6 we have the option to go to value number 8, and we also have the option to go to value number 9. From this 2 we have the option to go to value number 6, and then 6 we have the option to go to value number 9, and currently we are located at this position. So these are the possibilities, or these are the options we can have. Let's assess each path. So in this case, if we go from 1 to 6, then from 6 we can either go to 8 or we can either go to 9. In either case, the answer for this portion is going to be value number 3. But in this case, if we decide from 1 to 2, 2 to 6 and 6 to 9, we are going to get the answer to be of value number 4. So in this case 4 is the maximum answer we can get, but we don't actually have to do all of this computation. Why? Because we are using dynamic programming. That is the most important concept so far. So from this value number 1, the moment we see that this is where we can go, our mind should click that if we take this path, then what we would do is from here if we take this path, then the sum is going to be 3. But from here, if we take this path, then the sum is going to be 4. So obviously we are trying to find the maximum value, so we are going to store the value 4 rather than storing the value 3, and 4 is here. Now we are again located at this value number 1. From this 1, can we go over here? No. Can we go over here? Yes. So what is the maximum path we can make? We can do one jump like this, and we already know that there is only one single entity path we can choose over here, so maximum value we can get is going to be 2. So this is going to be our dynamic programming graph combination matrix combination solution, and that is why this is treated as a hard problem. But in my opinion, if you already knew these concepts, then it won't be so difficult for you. And after watching this video, I can guarantee that this is definitely not going to be hard for you. So we can clearly see that in the end we only need to return the maximum value that is present inside the dynamic programming graph, and that we can return quite easily, and this is going to be the whole solution. Now this is a very beautiful solution. If we see time and space complexity in this case, essentially the time complexity is going to be big O of 2 times m cross n. So overall we can write the time complexity to be big O of m multiplied by n, which is a very good time complexity. And if we see space complexity, well, this is a little bit more expensive because we are using an additional 2 by 2 or m cross n matrix over here. So this is also going to be big O of m multiplied by n, but this is also reasonably acceptable. This is not very complicated. So in my opinion, this is a very good problem to understand 3 major concepts, and that is graph, dynamic programming, and also matrix. So everyone should do this problem at least once. Now let's go to the coding part that is not so difficult. So basically, first of all, we are going to create a 2D array to store all the directions that we are going to traverse over. We are also going to have some private integers that we are going to use. Now the first idea is to create or to find the longest increasing path. As an input, we are using the matrix that we are given in the input, and we are simply going to iterate over the given matrix. We are also going to create a cache or a dynamic programming m cross n array, and we are simply going to have our answer stored initially as value number 0. Then with using 2 for loops, we are going to iterate our n cross n array, and we are going to check that whether at any single cell position are we finding the maximum longest increasing path or not. And to do that, we are actually going to call another helper method called dfx, where in the dfs as an input we are going to provide matrix, the current ith and jth position, so to identify that which cell we are talking about, and the current array that we or the current dynamic programming matrix that we have created and populated. Now inside our DFS method, we are first of all going to check that for any particular value, are we or have we already checked that particular cell value or not, and we are going to initialize the dynamic programming array as 0. So if the value is not equal to 0, then we need to find the value for that, and we are now going to iterate in all four directions from that particular cell. Then we are going to check that we are going out of bounds or not using these four conditions. If not, then we are only selecting the path where the adjacent values are going to be in the increasing order, and if that is the case, then we are going to update the value of our current cache with whatever the maximum value we can find for that existing cache, or recursively calling the DFS method again. And in the end, we are going to add one more value to our cache because we found an additional path that exists. And let's say if we don't find any additional path, still the initial value of cache is going to be 0. So if we increase it by 1, it is going to be added by 1. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to a lot of other solutions. I would be posting this code in our GitHub repository, and that link for our GitHub repository is actually posted in the description, so you would be able to check it out from there. Thank you. Hello friends, so the LeetCode problem we are going to solve now is called distinct subsequences. We can see that this one is a LeetCode hard problem and also a very well-liked problem. Now basically we are given two strings s and t in the input. Now we need to return the number of distinct subsequences of s which equals to basically t. So how many different ways we are able to generate string t from the given string s, and that is what we need to return. So let's try to understand it with a couple of examples. Let's say that we are given the string as a b b and the given string is a and b. Now in this case, notice that we can generate t in two distinct ways. First one is if we use just this first to ab, or second one is if we delete this ab and we use the first and last ab. So that is what we need to return as the answer. Second scenario is that let's say if we are given the word rabbit, RABBBIT, and in the subsequence that we are trying to generate is RABBIT. So in this case we are dealing with 3 b's over here, and over here we only need 2 b's. So basically once again we can generate it using 3 distinct ways. First way would be where we are eliminating or not considering this b, so that forms rabbit. Second scenario would be where we delete this b, and third scenario where we would not consider this b, and in either case we would be able to generate t, so we can return the answer. Now as always, let's try to understand the brute force solution first. Well, we know that at any given character s, we need to define that will that character help us generate value that is currently present in t. So for a smaller example, let's say the given values a, b, b, the current t that we are trying to generate is a and b. Now notice that at any given location of s, we are making two decisions, whether to include this a or exclude this a in order to generate the t. If the characters match, we include it for our subsequent answer. If they do not match, we could have excluded it and then try to see whether some other sequence makes sense or not. Same way, after doing this, even for the other two characters, we still have the same two possibilities on whether to include this character or not. And very quickly we realize that this leads to basically exponential time complexity, where we are dealing with somewhere between, like, I guess 2 to the power of n time complexity, where n defines all the characters that are currently present inside the given s, and 2 because we are making two decisions at any given interval, which is a very expensive time complexity if you plan to solve this. So we'll have to find a better way to compute. Now just try to understand that the optimal approach in this case is going to involve the most beautiful approach in the entire computer science, and that is going to be dynamic programming. But the thing is, let's first understand that why do we need to use dynamic programming in this case. Well, because all the values that we have currently calculated so far are going to help us make future decisions. Let me give you an example. Let's say the given values are a, b, b, c, and the value we are trying to generate is going to be A, B and C. Now notice in this case, if we have already computed that in order to generate this character A, there is only one way we could do it, why don't we just keep that information handy? So next time when we encounter character AB, we don't have to look the entire ways to generate AB from the given input. We already know for a fact that this are, like, let's say there is only one way to generate A, we know for a fact, and then we found like 2 or 3 occurrences of B, then in either case for each of the occurrence we can recompute that result. So let's say that since we are given 3 B's over here, we know for a fact that there are going to be 3 distinct ways for us to generate A, B, no matter what. And now when we are dealing with C and we realize that there is only one C over here, which means there is only one way we could do it, which means it does not add to us being able to generate this value. So overall the answer is going to be 3. But let's say over here, if we are also dealing with 2 C's and a D, then also the answer might change. So at any given instance in the character that is currently present at T, we define that whether that character matches the subsequent character inside the S or not. And based on that, we are trying to check that what has been the previously calculated results for each one of the characters, and then we are able to make that decision on whether to include that character or not. Now notice in this case, the number of subsequences only increase when the characters match, and basically when we have already calculated all the values that we have calculated so far. Because over here, if this was ABC and ABC, we know that there is only one distinct character. But if this was ABBC, then we have a match at B and one time and a match at B at the another time. So basically we can take whichever B path we want and the answer would still yield the same result. So that's why we are dealing with two possibilities over here. First possibility is if there is a match. If there is a match, basically we include both the possibilities of calculating or both the paths that would yield us in a subsequent. If they do not match, then we simply do not need to include that, and we can keep the same subsequence number that we have even if we did not included that character from the given subsequent S, because it wouldn't change the total number of result that we are trying to generate. And we would understand this if when we start using a DP matrix in order to solve this problem. Now the question becomes, why do we need to use a DP matrix? Because the characters present in S and the characters present in T, they both are of value to us, and we will have to calculate for every single possible permutation combination. And in the very last result that we find in the matrix, that is going to be the total number of distinct subsequences we can make. So I have currently drawn a big matrix like this. Now notice that all the characters we have in the T are currently present over here, and all the characters in S are currently present over here as part of this. So this is going to be basically our jth value, and this is going to be basically our ith value. Now we know that this is going to be a dynamic programming solution. Also, for any DP solution, we need two things. We need a base case. So base case is going to be quite straightforward. It would be as if the given S is not present, or if the given T is not present, what is going to be the value? We know that if, let's say, that T is not going to be present, which means there is only way for us to generate T from the given S is not to include any characters, because that is also a subsequence of given S. So all of these numbers would only mean value number 1. So we can just mark them as 1, because if the character in S is present but subsequent T is not present, we can only make one subsequence out of it. Let's understand vice versa. If the given S is equal to null, but we still have some value present inside the given T, which means we would never be able to generate T based on the given S, because the given S is empty. So because that is the case, then all of this results are going to be 0, because we are not able to generate T, or we are not there does not exist any subsequence that would be able to form T from the given S. Okay. Now we know that what needs to be the recurrence relation. So recurrence relation is going to be quite straightforward. For any particular ith and jth value we are trying to calculate, we would see that if they match or not. If they basically match, we will have to do the sum of both the subsequence, which means we would need to consider that what does the diagonal value for any particular character is. So that is going to be, let's say for I and j, if they match, then the diagonal would be I minus 1 and j minus 1 plus what the previous subsequence has been with respect to s, and that would be the value I minus 1 and the current jth value. We'll have to do the sum of both of these two characters. So let's say that for an example, we notice that this a matches this particular a. So because this cell has a match, then we'll need to combine the subsequence we are able to generate over here plus the subsequence that we have been able to generate over here, because we can take both the paths from here. And notice that only the values of I differ, j would remain constant because we are trying to build t from the given s. Now I know it sounds confusing, but we'll understand it when we move to building our matrix. Now the second scenario is that if they do not match, then simply that does not add any value for us to build a subsequence. Let's say over here this a and this b do not match. So because they do not match, they are going to have the same number of distinct subsequence value that we calculated even for the previous result of I, that is going to be the cell above it. So we will just replicate that value. So if they do not match, basically we will just take whatever the value of I minus 1 and j was as it is, and we will store that in the result. So now based on this two recurrence relation, let's see that what does our distinct subsequence that we are able to find. We notice that there is a match over here, r and r, they do match. So because they do match, we are going to take the sum of the diagonal value and the top value. Now notice diagonal is also going to be 0 for the first value, so we'll just mark it as 0, and sum of this two is going to be 1, so we'll mark it as 1. Same way for this r and a do not match. Because they do not match, we are going to carry forward the value from the top, so this would become 0. Same way r and b do not match, so this would become 0, r and b do not match, so on and so forth. So all of this are going to be 0. Okay, now a and r, once again they do not match, so we will take the value from the top. Now over here in this case, a and a actually match. So for this cell, because they match, we are going to do the sum of this character plus sum of this character. So let's just mark these value as 1 as well. Once again, a and b do not match, so this is going to be value from top, and so on and so forth. We will just mark all of these values as 0. Now for b and r, they do not match. So because they do not match, value from the top 1. B and a do not match, so once again value from the top as 1. B and B do match, so because they do match, we are going to do sum of these two values, so the answer is going to be 1. Okay, once again B and B once again match, so sum of these two are going to be 0, and once again B and B do match, so sum of these two are still going to be once again B and I do not match, so value from the top, and then B and T do not match, so value from the top. Now B once again, so this is going to be value 1 1 so far, but now this, notice that this B also matches this B, so in this case we are going to do sum, so this would become value 2. Now once again this B also matches this B, so once again the sum is going to be value number 1, and now so on and so forth. These are going to be 0 0 as it is. Now for this third B, once again this is going to be 1, this is going to be 1. There is a match with this B, so because there is a match, I'm going to do sum of previous two elements, so this is going to be 3. Once again for the subsequent B, once again there is the sum, so this is going to be 3. So I'll add those values, and now this value is I, so they do not match, so value from the top 0, and once again T do not match, so value from the top 0. Okay, now I'll change colors again, so better visibility. For I, basically all of these values do not match, so up until that point we can just carry whatever value we had from the top, but now this I matches this I, so we are going to do sum of these two values, so total is going to be 3. Once again this T do not match this I, so once again the total is going to be 0. And lastly for this T, last time we are changing the colors, and basically the value is going to be same that we have been able to identify all up to this, but this last T matches this last T, so basically the sum is going to be these two, and the answer is going to be 3, and this is what we need to return as the answer. So basically you understand that how using dynamic programming we were able to shrink our solution from 2 to the power of n to basically time complexity of big O of m multiplied by n, where m is the length of s and n is the length of t. So which is a very good time and space complexity. We cannot go any more optimal than this. Now in terms of space complexity, because we are using an extra matrix, this is also going to be big O of m multiplied by n. That is a reasonable cost to pay. So now let's understand the coding solution for this. The coding solution is going to be quite straightforward. First, we are going to define two variables m and n to take care of the length of the given subsequent s and t strings. Then we are going to initialize a 2D dynamic programming array, and basically we are taking it as m plus 1 and n plus 1. This is to take care of the base case. Okay, after that we will initialize for basically when the given I and I is equal to 1 and j is equal to basically 0. So for the first column, all of those values are going to be 1 and all the jth column is going to be 0. We haven't mentioned it over here, but that would be like an intuitive thought that we can understand. Now we'll start filling in the dynamic programming array. We will check that for the given dynamic programming array, if the characters match, then we are taking in the value from the diagonal and the value from the top and summing it up. That is going to be our subsequences. If they do not match, we'll just directly inherit the value from the top of the DP matrix that we have calculated so far. In the end, we will simply return the result or the very last cell in the DP matrix. Coding is not that much, but concept is quite important. Let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats nearly 65% of all the other solutions, which is pretty awesome. In terms of space complexity, we could have done things slightly better, but anyways, this is also a reasonably good space complexity. Once again, the coding solution is present in our GitHub repository, so feel free to go and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So the LeetCode problem we are going to solve now has to be one of the most difficult problems that I have solved so far. It's called burst balloons. We can see that this one is a LeetCode hard problem and very justifiably also a very well-liked problem. So basically we are given n balloons that are under indexed from 0 to n minus 1. So they can be placed in an array. Now for each balloon is painted with a number on it. That number is represented in an array called nums, and we are being asked to burst all of these balloons. Now the number that is currently written on that particular balloon represents like some sort of coin values. But the thing is, when we burst a balloon, we actually get coins in by multiplying its neighboring cells with that particular number. And then neighbors basically change because we already burst a balloon from in between, and then we keep on repeating the same process. Our aim is to make sure that we can receive maximum number of coins by bursting as many balloons wisely. So this is the key phrase. Now we are being told that let's say that we run into an issue where there is a neighboring cell that is at the edge of the given nums array. Then basically just imagine that there is one neighboring cell with 1 painted on it, so that we don't run into an issue of array being out of bounds. So let's say that we are given an example of 2 balloons. The values are 1 and 5. Now notice for these 2 balloons, basically we can treat them as following, where the middle 2 balloons are still going to be values 1 and 5 as represented over here, but it is going to have 2 neighboring balloons that are valued 1 and 1 that we are not going to burst. We will only consider these 2 balloons, but they are there for us to our support. Now what is the maximum value we can achieve? Now let's say that we decide to pop balloon number 5. If we pop balloon number 5, basically we get value such as multiplication of its neighboring values. So it would be 1 multiplied by 5 multiplied by 1 because of these 3 values. Now notice this would yield us the result 5. Plus we still have one more balloon because we already popped balloon number 5. We would have one more balloon 1 that needs to be popped, and now its neighboring cells would become 1 and 1 and with 1. So this would become 1 and this would total out to 6. But the thing is, this is not a wise approach. Why? Because in the same example, if we notice that instead of bursting balloon number 5 at the beginning, if we decide to burst balloon number 1 in the beginning instead, then basically our values would be, so we burst this balloon number 1, so that would yield us the value of 5 multiplied by 1 multiplied by 1, so total would be 5. Plus now this balloon no longer exists, but we still have this 5 left, and its neighboring balloons are 1 and 1, so this is also going to be 5 plus 5, so total is going to be 10, so we need to return 10 in the answer. Let's say same way we are given the values 3, 1, 5, 8. Now in once again for this example as well, we can choose wisely, and the most logical way to pop balloons would be that if we decide to pop balloon number 1, if we decide to pop balloon number 1, we would get values 3 multiplied by 1 multiplied by 5, and the remaining balloon would be 3, 5 and 8. Okay, so let's sum up this value. So this is going to be 15. So 15 plus these three values. Now once again in this case, and remember, imagine that there are going to be two neighboring ones present at all the times. Okay, now once again we would decide to pop balloon number 5. If we do that, we will be doing 3 multiplied by 5 multiplied by 8, and the remaining balloon is going to be value 1, 3, 8 and 1. Okay, now once again in this case, this is going to be 15 plus this is going to be 120 plus this is, now in this case the ideal thing would be to pop balloon number 3. If we pop balloon number 3, then we get value 1 multiplied by 3 multiplied by 8, so 24, and then we would no longer have 3 existing, so last value would be 8 remaining with 2 adjacent ones, and that would be plus 8. And if we do total of all of these values, the maximum number we can achieve is going to be 167, and this is what we need to return in the answer. So I hope this long explanation makes sense that what is being asked for us to solve this problem. Now, very first approach comes to our mind is a typical brute force approach, that if we are given n number of inputs, let's say values 1, 2, 3, 4, right? Why don't at every given position we have the 3 option of choosing whether to pop that balloon or not to pop that balloon. So if we decide to pop balloon number 1, then we are going to be left with the value that we received from balloon number 1. So that is going, let's say that the value is x, plus we have the possibility of dealing with the remaining 2, 3 and 4 values. And once again in this path, once again we will have the option to take this x, plus amongst 2, 3 and 4 we can pick a number. So let's say we decide to pick balloon number 2, so that value becomes y, and then once again we are going to be left with values 3 and 4, and once again we will be making a decision. Same way for every single value we can make a decision based on the sequence of balloon we pop, and same way we are going to have different choices, and subsequently it will grow over period to basically all of the different permutations and combination of choices we can make. So that is going to be a very huge decision tree that we can make. Now in this case the answer is going to be 2 to the power of n, where n is the total number of characters present, because at every single instance we are deciding whether to include that or not to include that. So that's a very expensive time complexity. That doesn't work. Let's try to become greedy in our approach. So greedy approach works something like that. Basically we can take an input and we will try to pick the smallest value. So let's say that we saw in the example of 3, 1, 5, 8 that we would pick the 1 first because it was the smallest value, so it would not bring any like long-term benefits to us if we just keep it around. So why don't we burst balloons with the smallest value possible? So in that case, if we decided to burst this balloon number 1, let's say being greedy, okay, so we get the value as 15. Okay, plus now we are left with 3 values, 3, 5 and 8. Once again logically we would be bursting balloon number 3. So if we do that, once again we would be generating the value as 3 multiplied by 5 multiplied by 1. So this would become 15. Plus same way we would be left with value 5 and 8. If we do that, we will be bursting value number 5, so the value would be 40, and plus lastly there would be value number 8, so this would become 8. So if we do sum of all of this, it's going to be 30 plus 40, 70 plus 8, 78. So greedy approach also doesn't work, because we know that if we can do it wisely, we can solve this problem and gain 167 coins amongst this input. So this is also a second choice that would not work. So now the solution would become pretty obvious to you. So in this case, we are actually going to be using the most powerful and beautiful concept of the entire computer science, and that is called dynamic programming. Now, how we are going to be using dynamic programming is that, remember in the brute force approach, basically when we had 4 inputs, we would take certain paths. So we would pick what if we burst balloon number A, and then we are left with whatever the value we generated from balloon number A plus whatever value we can generate from B, C, D. Same way, once again we have two choices of A plus B plus whatever value we generated from CD. Same way over here, we could have decided to burst balloon number balloon number B, and then once again generate the value that would be gained from A, C and D. And once again we could have burst balloon number A, and then once again the values would have been C and D. Now notice that both in this case we are left with value A plus B plus CD and A plus B plus A plus CD, basically in just reverse sequence. So we need to keep track that at every given moment, whatever the balloon we burst, depending on whatever the range, what is the value we are generating. Now important phrase over here is going to be range, that we need to know that between every single combination of values, what maximum coins that we are able to generate. Now in this case we'll need to do we'll require a 2 by 2 matrix. Now notice in 2 by 2 matrix I'm using the same example we used 3158, but we have added one at each of the end. They are just denoted by different color, and they are to make sure that we have a neighboring cells present, but we are always going to be iterating amongst these 4 values. Okay, so when I talk about keep track of the values of bursting balloons, that would be amongst this set of values. Now one more thing is, let's say that I only give you value number 3 and ask you that what is the maximum balloon I can generate. You must be saying that, hey, it's pretty straightforward. We would do like 1 multiplied by 3 multiplied by 1, and total is going to be 3 for sure. Now let's say that I give you value 3 and 5. Now what is the maximum possibility? Well, we have two possibilities. One possibility is that we actually take 3 first, so basically that would become 15 plus 5, or we could have taken 5 first and that would have become 15 plus 3, so greater total is 20. So we can say for a fact that if we are dealing with only 2 balloons with value 3 and 5, maximum value we can generate is going to be 20. Now in this case, let's say that we add one more possibility, that 3, 5 and 8. Now for this fact, we can say for with certainty that with this 8, the maximum value amongst this 3 and 5 we can generate is going to be 20. So we can leverage that fact and we can use it to our advantage. In this case, there is also possibility that instead of taking 8 at last, we can take 8 somewhere in middle. So we'll need to keep track that what would be the value being generated with the value 3 and 8, and we'll have to keep track of all of these different permutations and combinations of values. So that's why we need a 2D matrix and a sequence of range that we are going to be determining. Now in this case, let's just try to do it one by one, starting with the smallest range possible, and that is going to be of interval 1. So let's say if we are only dealing with interval 1 ranges, what are the different values that we are trying to compute for? First value would be 1 1, second value would be 2 2, third value would be 3 3, and fourth value would be 4 4. Okay, now for 1 1 we are thinking that if this were to last value that we are going to be bursting, what is going to be the result? So basically because range is 1, remember, so we are only incrementing the neighboring cell by 1. So in this case 3 multiplied by 1 multiplied by 1, so the maximum value we can generate is going to be 3, so we will mark it over here. Same way in this case, let's say that for some reason we decide that instead for 2 2, so for 2 2 this is the value that we are talking about. What is going to be the maximum value we can generate? The neighboring cell, so remember that we have decided that we have burst all the neighbors in that range, but because this range does not have any value other than that, these are going to be the neighbors. So this is going to be 3 multiplied by 1 multiplied by 3, so that is going to be 15. So we can mark 15 as it is. Same way for value number 5. Once again, there are no neighbors, so 1 multiplied by 5 multiplied by 8, so that is going to be 40. And same way for value number 8, once again, 5 multiplied by 8 multiplied by 1, so that is going to be 40. So we can mark all of these values as it is. That's cool. Now let's up the ante and let's update our total number of range that we are currently trying to build out. So first range would be of size 2. Now comes the interesting part. Now what are the ranges we can generate? So range would be 1 to 2, second range would be 2 to 3, and third range would be 3 to 4. Now let's talk about just range 1 to 2 for a moment. Now in the range 1 to 2, we are talking about basically these two values, 3 and 1. Okay. Now 3 and 1 amongst the grand scheme of total 3, 1, 5 and 8 amongst these four values. So now notice that we have the two choices. First choice is that 3 would be the balloon that we would pop last, or 1 would be the balloon that we would pop last. What if we decide that 3 would be the balloon that we are going to be bursting last? Then in that case, what is going to be the neighbor of 3 that we would multiply 3 with? Because we have already popped 1, so that would be value number 5. So that would be 1 multiplied by 3 multiplied by 5. This 1 we got from the neighboring 1, that is this over here, and 5 we got, that is the end of the range, that is the over here. Plus we must have received whatever compensation we got by bursting just balloon number 1, and that is going to be dp of basically 2 and 2. So this is that is this value. So the maximum value we can generate is 15. So in this case it's going to be 15 plus 15, so maximum value we can get is 20 for range 1 to 2 by bursting balloon number 3 last. So one possible value is 20, so let's just mark 20 as it is right now. Let's just come back once again, do our calculation. Now for the same scenario, we are considering that what if we decide to burst balloon number 1 last. So okay, so 3 and 1, we are bursting this balloon number 1 last, which means we have already burst this balloon. So what is going to be the neighboring cell? 1 and 5. Now what is going to be the value? So bursting balloon number 3 would give us maximum value of 3. So let's mark 3 plus bursting this balloon number 1 now would be 5 multiplied by 1 multiplied by 1. So that is going to be 8. So 5 and 8. Yeah, so basically 5 plus 3. So total is going to be 8. So in this case, because the higher value is going to be the maximum value that we can generate, that would be amongst this. This value was supposed to be 30, not 20, because remember we did 15 plus 15. Okay, so now the maximum coins that we can generate at between range 1 to 2 would be amongst the maximum between 30 and 8, and we know that maximum value is going to be 30, so we will just mark 30 over here. This defines that this is the maximum number of coins we can generate for this particular range. Now let's just come to the next range in our set of sequence, and now I'll just start moving quickly because I don't want to spend this much time for each of the things. Okay, next range would be value 2 to 3. So now 2 to 3, the values are going to be 1 and 5. Okay, now for this one, what if we decide to burst balloon number 1 first? Sorry, balloon number 1 last. If we burst balloon number 1 last, basically it's going to be value number 3 multiplied by 1 multiplied by 8. So that is going to be 3 multiplied by 1 multiplied by 8. So that would be 24 plus whatever the value we get from DP at value 5 and 5. Value 3 and 3. So that is value 3 and 3 is going to be 40. So the sum is going to be 64. Okay. Now what if we decide to burst balloon number 5 at last? So in that case, it's going to be 5 multiplied by 8 multiplied by once again 3. So plus whatever value we get by bursting this balloon, so that is going to be 15. So the total is going to be 135. So logically it makes sense that at range 2 to 3, the maximum value we are able to generate would be value 135. So we will just mark 135 as it is. Okay, now the last range we have is going to be range 3 to 4. Now once again at the values range 3 to 4, what are the basically two balloons that we are able to pop? The values are 5 and 8. So we can either pop value number 5 in the last. If we decide to pop value number 5 in the last, basically we would be gaining the value 45. If we decide to burst value number 8 in the last, we would be gaining the value 48. Now why did we get 48? I'll just quickly explain. Basically we are doing 1 multiplied by 8 multiplied by 1. So this is 1 and this is the second one, because remember we are talking about this range, and plus whatever value we get by bursting this balloon, so that would be 40. So basically 8 plus 40, so that sums up to 48. Okay, so maximum value is going to be 48 between the range 3 to 4. So we'll just mark it over here as 48. Okay, now same way, now we took care of all the intervals of size 2. What about all the intervals of size 3? So once again, for this one, the complication now becomes even more critical, because now the first range we are talking about would be 1 to 3. So we have the three candidates, 1 2 3 would be 1 2 and 3. So now we have three candidates, basically 3 1 and 5, to solve this answer. And for each of the one, so we have, what if we decide to go each of the one in the end? So I'll just do calculation for one of the values, for value number 3. So basically this would, what if we decide to go with this value at last? Now remember, 3 would be multiplied by 8 and it would be multiplied by 1. So it would be 1 multiplied by 3 multiplied by 8, because we took care of the entire range. Okay, plus now because this is the first value in the range that we are talking about, we would also need to do the dynamic programming of range between this value 2 and 3. So 2 and 3 we already have the answer, and that is 135. So this would become 135 plus 24. So the total is going to be 159. Okay, now what if we decide to burst balloon number 1 in the end? Once again, that value is going to be 51. And what if we decide to burst balloon number 5 in the end? The value is going to be 70. So 159 is the obvious choice. So between the ranges 1 to 3, the maximum value we can generate is going to be 159. So we'll just mark 159 as it is. Same way for the range 2 to 4, the maximum value that we are able to generate would be once again value 159 as well, by the same logic. And so we'll just, from 2 to 4, the value would be 159 as well. So we'll just mark it as it is over here. And now comes our final range, that is of range size 4. And for the range size 4, the only possibility in this case we are going to have would be basically just one value. So the range would be from 1 to 4. We have the possibility of bursting 3 1 5 and 8, all 4 balloons at the last. What if we decide to burst balloon number 3 last? If we decide to burst balloon number 3 last, basically the coins we would be generating would be 3 plus whatever the range we can get. So basically 2 3 and 4. So dp of 2 to 4. So dp of 2 to 4, we already know that value is 159 and plus value number 3. So that is going to become value 162. Okay. Now let's do the calculation for value number 1. So basically, once again, for value number 1, the total would be 159 plus the total sum would be for value number 1, the total would be only 52. And why it would be 52? Because remember, this value, the range would be so for this one, value number 1, the range would be, basically we would do multiplication. So that is 1 multiplied by 1 multiplied by 1. So that would be 1 plus, remember we have two ranges. First range is dp of 1 to 2. So dp of 1 to 2, and second range would be dp of 2 to 4. And dp of 3 to 4, because we already took care of dp of 2. So this dp of 1 to 2 is going to be 30 plus dp of 3 to 4 is going to be 48. So 48 plus 30 plus 1. So whatever the value that would come up to. So on and so forth. If we keep on doing, basically the maximum value we are going to be getting would be for value number 8, because remember, for value number 8, the multiplication would have been 8. Okay, let me just clean this up a bit. And I know that this video is getting super longer, but it is what it is. Okay, for value number 8, basically the multiplication is going to be 1 multiplied by 8 multiplied by 1 by ignoring all of these values, plus dp of range 1 to 3. So range 1 to 3, the value is 159. So 159 plus 8, so this would become 167. That would, we would store over here, and this is what we are looking for, that what is the maximum value we can generate between range 1 to 4. That would be 167, so we can return that as the answer. I know this was a super long video, perhaps the longest one that I did for dynamic programming, but it's an important one. Now let's analyze the time complexity. We'll have to iterate over n by n matrix basically, so that would become big of n square work, and for each of the ranges we will have to do it, so that would be multiplied by n, so that total time complexity would be big of n cube. There is no other way to do it faster than this, even with using the dynamic programming. And space complexity is going to be big O of n square, so which is a reasonably good time complexity given how complex this problem is. So now let's quickly see the coding solution for this one. Now the coding solution is slightly straightforward. So basically we are given total length n. Based on that, we are going to be generating our extended array that is going to be of size n plus 2, and we are going to be adding the last values as 1, that is to take care of the neighbors. Then we are going to be iterating over the original nums array and add values to our extended nums array. That would be for simplicity for us to update all of the values. Now we will generate our dynamic programming array, that is, notice that the values is n plus 2 and n plus 2, that is to take care of the two neighboring cells. Now we'll start filling in our dynamic programming table and iterating over all the values. On top of it, we'll have to define a range for every single different position, and that is what this right length defines, that this is the range we are talking about. And at every given range, for every single range that is possible, we will calculate that what is the maximum coin we can achieve on that particular value. That would be by doing the multiplication of extended nums left minus 1 multiplied by extended nums of that particular value multiplied by extended nums right plus 1. Notice that we are taking the values that would be out of the range for every single value, and we are updating the value plus by doing the coins of dynamically programmed ranges that we have already found so far. So for any ith range, the value would be dp of left to I minus 1 plus dp of I plus 1 to the right, and we already have the values being calculated by bursting that particular balloon. And the range value at any particular location would be the maximum value that we currently have, or the new maximum value that we just found. Whatever is greater, we'll just store it in the result. So these are the 3 for loops that would take care of all the entire logic that we just explained, and then we can simply return the value for the range 1 to n, that is the range that we are given in the input. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats nearly 80%, like 74% of all the other solutions, which is pretty awesome. I would be posting this in the comments and in our GitHub repository, so feel free to go and check it out from there. Thank you. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to create free resources that will empower every single engineer in this world so that they can do better with their technical interviews. Now continuing in that direction, today we are going to solve a very important problem called regular expression matching. So let's get started with the problem. So if we see some of the popular companies who have already asked this question, there are companies like Microsoft, Amazon, Facebook, Google, Bloomberg, Adobe, Apple, Uber, Snapchat, Tesla, Goldman Sachs, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem. Basically, we are given two input strings. One is string S and the other one is pattern P. Now we need to implement a regular expression matching function that can support a dot character and a star character inside this pattern P as well. Now we are given the definition that what does a dot and a star represent. Basically, a dot can represent that it can match any single character, and the star represents that it can match 0 or more preceding elements. Now, first let's try to understand both of these with examples. So suppose we are given a pattern P that looks like A, B and dot. Now, dot by definition, it can support any single character. Now inside our given string S, suppose we are given the values to be A, B, C. Now can we conclude these two to be matching strings? The answer is yes. Why? Because for this particular dot, we can consider it to be C because it can match any character. Suppose if we are given an S that looks like A, B, X, is it true? Yes, this is also matching with this pattern P because for this time for this dot, we are actually considering it to be X. But if we are given S that looks like A, X, is this matching? No. Why? Because the second character over here, this is A. Meanwhile, the second character inside our pattern is B. These two are not matching, so this is not a matching sequence. So basically, this is what does a dot represents. Now let's try to see one example of what does a star represent. So basically, suppose we are given a pattern P that looks like this, where the values are again A, B, star. Now, what does the star is saying by definition? The star is saying that it can match 0 or more preceding elements. Now, what is a preceding element of this X? The preceding element is B. So, which means that now this particular pattern can match bunch of different other strings. So, strings such as A, B, 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 B. Does this match this particular pattern? Yes. Why? Because if we see, okay, first character A is matching each other. Now for the second character B, we can have multiple B's over here because of this star value, because that is what is given in the definition. So based on the definition, we are now in this case considering the star to be all of these B's. Suppose we are given a string S that is only A. Is this matching with this pattern P? Yes, this is also matching. Why? Because this star can represent that we have 0 or more preceding elements. So in this case, we are considering that we have 0 B's in the pattern, which means that our given S is actually matching. And in this case, since both of these are matching, now let's try to take one more example. Suppose our given S is equal to like A, B, X. Is this matching? No, this is not matching. Why this is not matching? Because this AB portion, this is matching, that is good, but we do not have an X over here, and that is why this is not a match. Does this match? And pause the video for a second, try to guess that whether this matches or not. Let me come up with the answer. The answer in this case is that this is actually a match. Believe it or not, this is a match. Why this is a match? Well, okay, first F is matching. This is good up until this point. Now, because we have a star with dot, which means we can have n number of occurrences of dot. And we know by definition that dot can represent any single character. So in this case, what we are going to have is, we are actually going to have 7 different dots. And these 7 different dots, they are going to represent each character that is missing in the remaining string. And then eventually when we reach to the end, we are going to declare this as a match, and we will be able to return true in each of the cases. So I hope after so many examples, things would make sense and you would get the idea that what this problem is asking us to do. Basically, we need to return a Boolean answer, whether true or not, that whether any given two strings, do they match or not match. Okay, now before we come up with the solution, first let's see that what could be the different possibilities for our problem and what could be the different things we can do in the solution. Now I have drawn a table over here where I'm representing different like string values and pattern values, and we'll try to see that what happens in every single scenario and what are the actions we can take. Now I have noted that there could be like a C mentioned over here in this column file, and this means that it could be any character from A to Z, because in the string we can only strictly have A to Z characters. Meanwhile, for the pattern we could have definitely C, or we could also have a dot and a star. So that means different things, and if they are present, we might have to do things a little bit differently. So first let's see the first scenario. In the first scenario, basically both the values we are given is like a simple character. So for S and P, suppose we are given the values like A, B, C and X, Y, Z. This is pretty simple to match that whether the string matches the pattern or not. We simply need to judge character by character. In this case, we can simply see that whether they are matching or they are not matching. This is a very simple binary operation. Second option we can have is the most beautiful option, that whether we are given one character and we are given a dot value. This is also very straightforward. If there is a dot present, definitely matches the character. We can simply return that there is a match for that particular character. Second scenario is that we could be given bunch of different characters, and we could be given like some characters at the beginning, and then we might be given like a dot and a star. In this possibility, basically what we need to check is that whether like a single character like this first character, and whether this first character, I mean this could this could represent like more characters. These could represent something like a and like a dot star, something like that, right? There could be like different matching things. I'm just noting down C. But this means that if like the before portion matches, everything at this position is definitely going to match. So in this case, if like the values before the dot and star matches, then everything is a match, right? If we take a look at this example, basically we are simply given dot and star. In this case, 100% there is going to be a match. Why? Because all the values that are present over here, we can take like 0, 1 or bunch of different dots, and all of these dots can represent all the characters that we have. Now comes the interesting part where we are dealing with a star. What could be different possibilities? So let me give you like one possibility. Suppose for this our string and P value, we are given the values like A, B, and over here we are given the values as A, B star. Question is this a match? Yes, this is a match. Why? Because this is the first value. This is a match in itself. And over here we only have one value of B. Now over here we have B star. So this B star could represent that we don't have any values, or we have one value of B, or we have two values of B, or we have infinite values of B all across like the board, whatever we want to choose. So in this case, we are definitely going to choose one value of B, which means this is a match. So in this case, what are we considering? Value before the like preceding value of star. So value before preceding value of star. If that is a match, definitely we can find a match, right? There could be another possibility. We could be given a string, we could be given a P, we could be given a bunch of different values like A, B, X, Y, Z, A, B, X, Y, Z. So far everything is a match over here. And then over here we are given something like 2, 3, 4, 5 Z's, right? And over here we are given like just a star value. In this case, how would you define that whether this is a match or not? Well, definitely this is a match. But the way you are going to define is that the values that this Z and star that we are considering, like these values, before that we are checking that whether all the values that are present before that, are they a match? If all of these values are match, definitely we can create this to be a match. So again, we are considering like all the values before the preceding value of star. I know I'm using a lot of abbreviations, but you just have to be with me. I'm not going to write all of them. And if that is a match, we can consider this to be a match. There is also one more possibility where we actually do not need to consider this like preceding value at all. What could be a scenario? Suppose we are given string as is equal to like A, B, C, D, and over here we are given some P is equal to A, Y star, and then B, C, D. In this scenario, this is definitely a match. Why? Because for this Y star, we are considering this to be 0. If this is being considered as 0 values, which means that this is a match, and then all the other values, they are match. So we will find a potential match over here. So again, we are considering like if the value before the preceding star. If that is a match, then we can consider this to be a match. So now we are just like dealing with lot of possibilities where every single time for value inside the pattern, we will have to keep track of the value, like two value before that whether that is a match or not. And in order to calculate any single calculation, we are always checking that whether the values before us, are they matching or not. So this is a very good candidate for a dynamic programming solution. Why a dynamic programming solution? Because first scenario, we are definitely like using whatever the results we have calculated to check that whether the current result we are at, if that is a good or not. Second, already calculated results are going to give us the ability to decide that what do we do in the current position, because we are not only dealing with like simple characters, we are also dealing with like a dot, and we are also dealing with a star. So this is going to be really helpful. And we can use something like recursion to solve this problem, but that is going to complicate things. We are actually going to use recursion with DP, and that is going to make things much more easier. So let's try to take one example over here. And the question is, for a dynamic programming, we are not only going, because we are dealing with two different like string and pattern, it would be better to create a 2D matrix, and inside the 2D matrix, for every single like string and every single pattern, we will try to see that whether the characters match or not, and based on their true and false values, we would be able to calculate some interesting results. So let's see that in action with an example, and that would make things more clear. Okay, so currently we have created an example for a string and a pattern, and we need to check that whether they match or not. Now also for this pattern, I have created a 2 by 2 matrix where inside every single row represents the string value we have, and every single column represents a character inside the pattern we have, and we will try to see that whether there is a match or not. Now remember, for the first row and column, I have kept it as empty. Why? Because these we are going to use to create our base case. Now our base case is that currently for the string, the first character we have is empty character, and also for the pattern, the first character we have is empty character. Now, because these two are empty characters, definitely empty characters are going to match for sure. So in this case, this value is always going to be true. Now we will try to see that whether there is a match over here or not. So in this case, because this is an empty character and we have some character over here, there is not going to be a match. So definitely we would always be able to like have all these values as false. So currently we are at this first position. This value is f, this value is f. Both of them are characters, both are same. And when both are same, we will also have to check that all the values before that, if they are also match or not. So currently the only values before that were two empty strings, and that represents this diagonal corner. So because this diagonal corner was true and we have matching set of characters, we are going to take the value that is diagonally present and put it at this position for this 1 1 box. Again, I'm repeating myself that because these two characters are same. So first we check, okay, these two characters are same. Then we check its diagonal value, because what this diagonal value is going to do is it is going to check that whether all the values before these two values, are they a match or not. And this will come in handy when we are at some position like this, because if over here we find this AA to be matching, which means this value is a true, but do we need to keep it as true? Because if this is false, which means if we are, say for an example, we have string to be FA and we have pattern to be PA. So in this case, though these two match, but this is not a match. Why? Because this F and P does not match. So we can break out immediately. And that is what we need to keep track of every single time. Then that is why this is a dynamic programming problem. So in this case, as explained, this is going to be true. Okay, now again let's start filling up this all of these files, and what we are going to do is, okay, this one is true. Now we will have to check that, okay, currently we have FA and the value we are comparing it against is F. Is this a match? No, this is not a match, so this is going to be false. Again, currently the value is FA star and the only value we have is F. Is this a match? Yes, this is a match. Why? Because for this a star, we can actually consider this to be an empty string or zero values of a. And if we do that, then we will have no values over here. So in this case, this f and this f is match. And why this happened? Because we had a star value over here and we were dealing with the star value. So now again the new theorem comes that whenever we are dealing with a star value, we will have to check the value before its preceding value. Again, whenever we are dealing with a star value, we will have to check the value before its preceding value. And if that is true, then we can directly mark true over here. So we check, okay, this was true. So definitely we are going to put true over here. Awesome. Now we are at this position number n. Now currently what is the scenario we are comparing? We are comparing the values of f, a, star, n, and we are comparing it with f. So n and f, there is no match. So definitely we can mark false over here. Now we add a dot over here. Again, there is a no match. So we can mark false over here. And same way, this is also going to be false. Okay, now we are at this position. So now we actually have two values, fa. Now for this fa, if we only compare it with this value f, is this a match? No, this is not a match. So we can mark false over here. Okay, now after marking false over here, currently we add this positions. Okay, so fa, definitely there is a match. So because these a matches, we will compare its diagonal value, and the diagonal value we get this result, and we will mark the value over here. So this is going to be true. Awesome. Now currently we are at this fa star. So fa star, is this a match with this fa? Again, now we have the star value. So we will have to check. First thing we will have to check is whether we can consider this to be just like an f and empty string, or we can consider this to be an fa, or we can consider this to be an faa. I'm talking about this value, right? And if we see this fa is a perfect match. So now because we have a star value again over here, we are going to mark this as true. But this true, we are getting it from the value before. Because remember, in this case, you must be wondering that, hey, for this particular position, this value is actually empty. Then why are we marking this to be true? We are marking this to be true because this one is true. Because we found a match of fa, and because this value is true, we will mark this as true. So let's do that. Awesome. Now currently the next value we have is like FAN, and this value we have is FA. So definitely there is no match. We will mark this as false, and if we add dot, we will again mark this as false, and blah blah blah. Right? These are all the values going to be false. Now currently we are at the position of FAA. Let me clean this up a bit. So currently we have FAA over here, and currently we only have f over here. So definitely this is going to be false. Again, this fa is also going to be false. Now again we are at the critical juncture. We have a star value. Now because we have a star value, you must be wondering that what will be the possibility. Well, the possibility is, again, over here for this fa star, we can consider it to be like only f, or fa, or faa. This case we are going to consider it to be faa. Now you must be asking that, hey, previously when we were at this position, you mentioned that because this is true, we are marking this to be true. Then when we were at this position, you mentioned that though this was false, but because this was true, we were marking this to be true. Now we are at this position. This is also true. This is also false. This is also false. Then how come we are marking this as true? We are marking this as true because this value is true. Mind blown. Yes, this is like the most important point for this problem, that whenever there is a star present, we will have to check three different values. So whenever there is a star present, we were checking that whether the value before the preceding value, if that is true, we can mark this as true. If there is a star present, we will check that whether the value before this, if that is true, then also we can mark it true. And if there is a star present, we can check that whether the value above it, if that is true, then also we can mark it as true. Which means whenever we were at this position, if we don't want to get into all of these like calculations, all we need to do is that currently we are at this box, then we will have to check three different boxes. First box is the right, like before box. Second box is this one, like the box before box, and third box is a box above that box. So for this particular box, if either this or this, if any one of the value is true, we will need to mark that value over here. If all three are false, then only we will mark it as false. And why this happens? Because this was a star value and there could be bunch of different possibilities we can use over here. And this was the most difficult part of this problem, and congratulations, you understood it perfectly. And now because this was true, now currently we have this FAA, and now we have this like F. Now we are at the next value, so next value is FA star n, and this n is not a match, so this is going to be false, and then all the subsequent values are also going to be the false. Now this is a very easy problem to tackle, because now we are at this position n, so this is not a match, so this is going to be false, this is also going to be false, this is also going to be false. And now we are at this n and n, because these both of these are characters, so there is a match. Because there is a match, we are going to consider it's like diagonal value, so diagonal value is true, so this is also going to be true. Now this is a dot value and we only have values up until this point, so which means we are going to mark this one as false, and we are also going to mark this one as false. Now again we are at this value number g, so we all of these are going to be false up until this point. Now there is a dot over here and there is a g over here, which means there is a match. So if there is a match, we are going to compare its diagonal value. The diagonal value is t, so that is true. So because this one is true, this is also going to be true, and the last value is going to be false, because we only have value up until g up till this point, and we have this m over here. Now the last value is, okay, this is going to be false, 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 and this is also going to be false. Now we are at this last position. This m is a match with this m, so because this is a match, we are going to take its diagonal value, and the diagonal value in this case is true, so we are going to take this value as true. Now our dynamic programming table is complete, and all we need to do is we need to check this diagonal file, and we need to check this last value. Because this last value was true, we can return true in this case, and this would be the answer we need to return. And that is the whole logic behind this problem. And this was a very beautiful problem. If we were only dealing with the dot values, this would be much easy to solve, but because we were also dealing with the star value, it added a layer of complexity. Now if we see time complexity, in this case the time complexity is actually going to be big O of m cross n, where m is the length of a string and n is the length of the pattern. And if we see space complexity, because we are creating a 2 by 2 matrix, basically the space complexity is also going to be big O of m cross n. And this is a beautiful solution, like one of the best dynamic programming solutions I have seen so far. So I hope you would have enjoyed it. Now let's move on to the coding. First we will check for an edge case, that if both the values are null, we can simply return null. If that is not the case, we are going to initialize our dynamic programming 2D array, and for this 2D array, let's name it as dp, and we are going to assign the length of whatever the length of s is plus 1, and also length of p plus 1, and we are going to assign the base value of the 0 0 to be true. And now let's populate the first row. So this should take care of the first column. Now let's start our loop. So we are going to iterate over I and j, which means we are going to do 2 for loops. Inside the loop, we are going to check for all 3 different possibilities. So first possibility is that the given characters, the p is actually a dot. If that is the case, which means it would be able to match any single character, we are marking like the dp of I plus 1 and j plus 1 to its diagonal value. Now you must be wondering, why am I dealing with like I plus 1 and j plus 1? Because for the first row and first column, remember, we mark their values as 0, and we actually started the value of s and p on the first position. So that is why every single time I'm going to updating like I plus 1 and j plus 1 values, because the ith and jth value is actually located at like 0 0 position. They don't have any values. So if there is a dot present, we simply check the diagonal value. Now the second possibility is that both of them are characters, and if both are characters and they both match, we can also mark their value as same as their diagonal value. Now we are at the third possibility, and the third possibility is that if the given character, if that is in the pattern a star, if that is a star, then we will have to do some additional calculations. So now for first we are at the value star. So there could be two possibility. We could have some value as like character and a star, or we could have some value as like a dot and a star. So if there is a dot and a star, we only need to check that whether all the values before that, if they are match or not. And if that is the case, we would be good. We can mark it as true. And so first let's take care of the scenario that if the given value is actually a dot star. So now we have done that check, and then we will check all of those three boxes I mentioned, that if either one of them is true, we will simply add that value over here. With this value, we are actually comparing all of those three boxes. So if any one of them is true, we can mark it as true. And in the end, this concludes all the possibilities we can do inside our loop. So basically we are done with our calculation. Now simply in the end, we need to return that what was the last value inside our dynamic programming diagonal. That should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's try to run this code. And our code runs pretty fast compared to a lot of other solutions, and which is really good. And it's great in terms of time complexity and also in terms of space complexity. And I would be posting this solution in the comments so you can check it out from there. Thank you.